Good. Okay, so I'm going to repeat what I said so it stays in the record. Right? Start with the syllabus. Hey, I uploaded a new version of the syllabus, and I start filling this column here of the schedule. You don't forget the estimated schedule. It may change as we go along. The important thing for this schedule is going to be the exam. The first exam is going to be next week on Wednesday, weekday on Wednesday. Chapters, I'm planning for chapter 15 through 17. Okay, let's see if we can, I'm quite sure we'll be able to cover every single till then. Chapter 17 will be, 15 through 17 will be with oscillations and waves, the chapters on waves. Today we are going to have this virtual lab, simple pendulum, and I will provide you with the data for the simple pendulum. Like I mentioned before, this is a very simple experiment, works very well all the time. Every now and then students make a mistake there, they don't get the data right, but it's an exception, okay? So, like I said, works very well. By the way, every lab here works very well that we do. Every lab that we do works very well. And now let's go back to our notes here, like this one. Let's look at this equation here. Okay, that's what we got for the amplitude. Okay. Reminding you, right? So let's see here. The solution for the forced oscillator is, it started right here. Yeah, that's the solution of the forced oscillator that we guessed. Okay, let me put the date here as well. Page break 6/15/22. Okay, we assume the following solution for the forced oscillator. Here you go. Upon substituting that in the differential equation, let's see, before we go to that, in the above equation, A and phi were unknowns initially. Upon substituting this gas, right? This gas in the differential equation, we found that this solution satisfies the differential equation, provided we have the following. Okay, so here we go. Provided we have this relation here for the phi, which was the first unknown that you got in the equation, and A. Okay. So this, because we came up with a solution for phi and A for unknowns that are reasonable, okay, that are real, that gives credence to our initial guess, to our guess for the solution. Okay, that gives credence. And not just that, but whatever we found here reflects reality. When we perform experiments, those solutions here reflects reality. Now, what I want to do This one here is rather easy to understand, right? If you want to find the angle phi, all you have to do is to invert this relation. The phi angle is going to depend on the frequency of the applied force, of the harmonic force. But there is one more thing here I want to tell you, and I'm going to rewrite this equation. Okay, notice that we have those two terms in those two constants, right? Let's take a look here. And I want to remind you one important thing. Here you go. Let's go back to the simple harmonic oscillator solution. Not the damped one, but this one, not this one is a simple pendulum, right? So I want to remind you of the result that we got for the SHM. Here you go, right here. Well, let me copy that here. I found it what I want. And it is, yeah, here you go. That's what I wanted, right? The solution is this one here. Here you go. This is the solution. The solution for the simple harmonic oscillator, right? Is something like that, and no resistive force, no resistive external force, is something like that. But I also told you that this term that you see right here is what? There's a name for this term here. Is the angular frequency. Okay, so let's rewrite that angular frequency. But I'm going to, because I am using omega. So remember, right? We have two angular frequencies here. One angular frequency is for the harmonic force. But now I'm telling you that we have also this angular frequency. I don't want to mix up those two angular frequencies. So instead of call it omega, the original one omega, I'm going to call this one, I'm going to rename it omega naught. Okay. So omega is the angular frequency, for the harmonic force. And omega naught is the angular frequency for the simple harmonic oscillator. Why am I doing that? I'm doing that because I'm going to rewrite those two equations that you have, okay? In terms of omega naught. That's why I'm doing that. Okay, remember?
Professor?
Yeah.
Pardon me for interrupting, but I'm late. I was having some connection issues. Zachary Blue, I'm here. Sorry. Just want to let you know.
That's it. Okay, good. Okay, thank you for letting me know. So, okay, so let's write down those guys in terms of omega naught. Okay, I'm going to start with omega naught square here. Oh, not this one. Yep. Ooh. Good. Omega square. Good. If we write that in terms of omega square, we get rid of square root. We get something like that, right? And then now we can here write K as being M omega naught square. Okay. M omega naught square, and I'm going to, substitute right in here. M omega naught square. Oh, little details about the software. Let's see if I can fix that now. Good. So M omega naught square right in here. The first equation for phi is going to look like that. And the second equation for the amplitude is going to be here written like that. Okay. So we go. This M can be factored out. Become M square. This M here disappear. Okay, and now I'm going to just summarize those two here in a simpler way. Okay, like that. Okay. What those equations are now being written in terms of the angular frequency of the force, of the harmonic force, and the angular frequency of the simple harmonic oscillator, of an oscillator undergoing simple harmonic motion, SHM, okay? Well, why am I doing that? There's a reason for that, okay? There's a reason. It's easier to picture what's happening especially in this equation. This equation is kind of straightforward, somewhat straightforward to understand what's going on. What a little bit difficult to understand what's going on is here in this formula, okay? Let us study the equation for the amplitude and see how it behaves. I did a similar treatment, I did a similar exercise in my physics 38 course, electricity and magnetism. And then basically I'm just repeating what I did there with different parameters. The equation is exactly the same. It's just that I'm replacing, some things with others. Okay. First, let us see what happens to the amplitude when there is no resistive force. No resistive force means the parameter B is equal to 0. Or no resistive force. No. The amplitude becomes easier to see this one for, and I'm gonna even label it A naught to distinguish from the most generic solution. Okay. So suppose now that we don't have any resistive force and just this harmonic force applied to the oscillator, how does this amplitude behaves? Keeping F naught M and omega naught constant and varying omega, how does the amplitude of the oscillator behaves? Okay, that's the question I'm posing to you. Let me go omega naught here. I'll make it nice by italicizing. All right. Well, it's kind of from this one here, it's kind of obvious that if omega is the frequency of the harmonic force, ends up being exactly equal to omega naught, what happens to the amplitude? The amplitude goes to infinity, right? That's what we call the phenomenon of resonance. You know, it's not that the amplitude goes to infinity, but it means that the spring that's attached to the mass just breaks up, okay? So engineers, when they build buildings and bridges, buildings and bridges, they behave just like harmonic oscillators, not simple harmonic oscillators, but oscillators that are under subject to a resistive force. And if you have a wind, okay, the wind can be thought to be the harmonic force that's being applied to the building. Have you thought about that? Okay, that would apply also to earthquakes. Okay, this model that we see here doesn't apply just to a mass attached to a spring, okay, which is the simplest type of oscillator that we can have out there, but it also applies to bridges and buildings. Whereas the outside force can be either the wind, or the force of a given earthquake. Okay. So if the angular frequency of the earthquake, for instance, matches the angular frequency of the building itself, okay, buildings are not rigid structure. They behave just like large pendulums, right, with a given oscillation. Then you run the risk of having your building collapse. Okay. Same thing happens to bridges subject to winds, and we do have a real case in which a wind managed to bring down a bridge there in Washington State. So engineers, whenever they're building bridges and buildings, they have to take this type of thing into account. Okay, so if omega equal to omega naught, then we have the phenomenon that we call resonance. If there is no resistive force, okay, no resistive force applied, in this case B equal to 0. So at resonance, the mass of your oscillator may not the mass, the spring, right? The spring of your oscillator will break down, and your mass will fly away. The same model may be applied, or may no, let's put can be applied to buildings and bridges subjected to an external force. The external force can be either an earthquake or wind, the gusts of the wind, the gusts of the wind. Gusts of a wind. Okay, so let's plot that in Excel. And then we're going to plot this one here. But we start with this one that's easier to understand. Okay. So let's go there and see here. Oh, what's going on here? Something happened here. Okay, now we're in good shape. I think I'm going to use this one. Let's use this one here. One more student coming in. Okay, so here you go. What am I gonna have here? I'm gonna have MK and I'm going to have omega naught and omega. I want you to practice that in Excel as well. Okay, it doesn't have to be Excel, can be also your favorite software if you want. I like Excel because everybody has it. Notes. Oh yeah, I need another one. Is F naught. Okay, if you wanna make it look good. Symbol. Oops. No. Another one. Here you go. Symbol. Good. And then I have to get lowercase here, subscript. Subscript, yeah. Same here. Good. So we have, apparently we have everything that we need. F naught MK, right? Omega naught, let's not forget that omega naught is the square root of K over M. K over M, I still didn't log it there. Let's say here it's gonna be 1 kilogram. 1 kilogram, here is going to be Newton per meter. Newton per meter, right? Yeah, Newton per meter. Let's see. Let's use 10 for now. And I'm gonna put here is going to be radians per second. And here's gonna be newtons. Let's see, let's put 1 Newton for now. And then we start with omega, radians. You know what? I'm going to do the following, copy it here and paste it here. Just let's start with 0 and then we're going to have an amplitude in meters. We're going to write down, but let's not forget is the A naught, right? The simplest one that we want to understand what happens with that equation. One more coming. The equation is, F naught. I'm going to put it as a constant. Square root M square omega naught square minus omega square. Oh, there is one more that I didn't put there, right? It's the B. Okay, let's go get it. Omega square. And let's see what I'm gonna do here. I'm gonna put in obviously the E. I'm gonna put E2 for the B square. Okay, now okay, the B is going to be Newton second per meter. Okay, let's start with one here. Let's see if we got it right. D2 is F naught. D2 is
Hey,
F.
Prof.
Yeah.
Hey, Prof. Hey, Prof. This is Lawrence.
Yeah,
I'm sorry, I
breaking
haven't
up
been.
since.
I think I had told you last time, but having trouble with my Wi-Fi. I'm having a little bit trouble with my Wi-Fi. I think I had told you last time, Prof. I'm just letting you know that they're working on the.
Yeah, if you have to send me a message and if you have to talk to me, make sure you send me a chat message, okay? So type there in the chat window, in the chat box, please. And so here you go. Let's troubleshoot what we have here, right? Here you go. D is F naught is square root mass square, okay? A square omega naught minus omega. Let's see, F is omega. That's good. That's square, and the B is going to be E. Okay, that's the problem here. E. Now, what about omega square? No, wait a minute. Not here. It's this one here. Right, E. Okay, we should have it right now. Okay, so here we go. F is going to be our variable, E is going to be our constant, so you put a $sign right in here. F is our variable, C is a constant, $sign, A is a constant as well. We put that $sign here. D is F naught. Let's see, looks like we got it right. Now, let's play a little bit with this angular frequency here for now. Okay. This angular frequency, see that? The angular frequency of resonance is 3.1. So we should have a maximum in the amplitude somewhere around 3 and 4, okay? Here you go. Yeah, that's what we have. See that? I didn't get exactly at this point where it's 3.1. So we can get, we can do the following. We can start at 2 and then 2.1. So you can see what happens nearby resonance, even closer to the resonance. Okay. So here you go, 3.1, right? Look at the amplitude. The amplitude is higher here. If we get exactly at 3.126, let's get this value here, 3.126, what you're gonna get? Oh, wait a minute, I put that, no, wait a minute. I forgot, this is supposed to be no, no resistive force, right? Okay, if there is no resistive force whatsoever, right? The amplitude goes to infinity right in here, division by 0. Okay? That's what we have. But you start to, if you start to have, you know, some resistive force, the amplitude doesn't go to infinity anymore, but it still goes to a maximum value. Still goes to a maximum value. Okay. If let's see, I put 1 here. Here you go. Okay, and so on, right? Let's see, 0.001. Huh? Yeah, here you go. 0.001, and so on. See, maximum amplitude at the resonance point, at the point of resonance. And we can plot some nice graphs using this data. Okay, again, I'm not getting exact resonance here, but we still can see that the amplitude is maximum there. This paint. Okay. So let's see how it looks like in a graphical format. I'm going to put even more. Here you go. Let's start with 0 again. 0.1, 0.2. Okay. So I'm going to put more data points in there. I'm going to populate with a higher density of points. We already went past the resonance point. The resonance point is anywhere between those two values. Look here. So let's see how it looks like. Don't forget, right? If you're talking about no resistance whatsoever, the amplitude goes to infinity at resonance. And I'm going to insert the graph right in here. We have very little resistive force. Okay, here you go. That's how it looks like. That's how the amplitude looks like. So what we are doing, we are changing the frequency of the applied force, the frequency of the harmonic force. That's what we are doing. Everything else is a constant. Everything else is a constant. M, K, the force, and this B here. If I keep on increasing my resistive force, what's going to happen to the amplitude? You know, just picture what's going to happen to the amplitude, right? The maximum amplitude is going to decrease, right? You go, see that? It's decreasing. I can even put here in the log scale and even put this guy here in the log. Here you go. So you can see better what's happening. It's not a symmetric curve. It's not symmetric. Okay. But here you go. Why it's not symmetric? There's a reason why it's not symmetric. Here is the case of zero resistance. Take a look right in here. It's not a symmetric curve. And if I keep on little by little increasing, okay, we can hardly see an effect there because it's in the logarithmic scale, right? Let me see if I can. Yeah, now we can see it because I went a large increase. Let's see, 0.5, right? The lower the B, the higher the amplitude at the resonant point, at the point of resonance. Okay, so 1, 2, and so on. We go back to the linear graph, right? Let's do it again. Here, 0. Okay, here you go. Look at the y-axis, 4.5, right? Let's see if we can get it. Yeah, now it's 3, right? It was 4.5, now it's 3. Now, if we go to 1, here you go. The limit keep on decreasing, right? 2, 3, right? 4, and so on. If I change the omega naught. I change the omega naught by doing what? I change the omega naught by changing the mass, for instance. The point of resonance is going to change as well. Let me go back to a slightly lower B here. So you can see, I want to see a sharper peak. Here you go. I like this peak. If I increase the mass, what's going to happen to the position of this peak? If I increase the mass, the omega naught is going to change, right? Well, let's increase the mass. Here you go. The omega naught shift to the left because I increased the mass. Remember that omega naught is directly proportional to K. If I increase the K, then the point of resonance is going to shift to the right. Huh? Here you go. See that? Omega naught is going to increase, and the point of resonance is going to increase is going to shift to the right, right? 30, and so on. 40. See that? And going back here to this guy, 1, yeah, increases, and so on. So that's very important that you have this picture of how a forced harmonic force affects the amplitude of an oscillator. Okay. So that's what I want to share with you. Okay. In order to understand physics, it's very important that you do this type of simulation, because some formulas are not easy to visualize, are not easy to picture in your mind. Some other formulas are pretty easy, right? Sine, cosines, we have, section. We already have a like second nature to the behavior of trigonometric functions, right? But some other relations are a little bit more difficult to visualize in your head, so you have to plot it in a graph. Any questions about that? Any questions about that? Let's see. I can play with the force as well, right? If I increase the force, we should expect to have a higher amplitude, right? Here you go. Higher amplitude. If I increase to 6, the amplitude is going to go to 9, I presume, because we double the force. Yeah. See that? So play with this computer program. Make sure you get the right formulas, and you will understand what's the behavior of the amplitude as you change different parameters. But the most important here is how the amplitude changes with a changing angular frequency of the force, of the applied force. Okay, don't forget angular frequency of the applied force, angular frequency of the harmonic oscillator, of the simple harmonic oscillator. If you are nearby the point of if you're nearby the point of resonance, here 4.47 in this case, because I changed the numbers, right? You should have maximum amplitude right in here. Here you go. Okay, so that's what we have for this one. Let me see how many students we have so far. 32 students. I want to take attendance. In this meantime, I'm going to update my roster because some of the students have dropped. Attendance right in here. Here you go. Forced oscillation. P39 lecture. Today is the 15th. Toby, are you there? Toby. Let's see if Toby here. No, Toby is not here. Harun, are you there, Harun?
Yeah.
Good. Musa? Musa is, let's see here. I think Musa is here, right? Yeah, just tell me that you are there, Musa, so I know that you're not away from your computer. Okay, good, thank you. Zachary Blue?
I'm here.
Okay. Elena Bosshart? Thank you. Let's see, Luis Cristo, are you there, Luis Cristo? Luis Cristo, is he, let's see. Yeah, looks like, oh yeah, it's still here. Okay. Not in my rosters. And Brian Spino. Brian Spino, let's see, okay. Let's see. Yeah, Brian's not in my list. Robert Faust. Are you there, Robert? I see Robert here in the attendance, but he's not answering, so I'm gonna put a star here. And Pedro Flores, are you there? Oh, here you go. Thank you, Robert. Pedro, are you there? Yeah, good. And Lawrence Flores. I don't see Lawrence here. Daniel Frady.
Here.
Thank you. Amalia Gale.
Here, Professor.
Thank you. Tiffany Wong.
Here.
Olivia Kruger. Thank you. Danielle Liang. Good, thank you. Anthony Lopez.
Here.
Thank you. Chuk Lu.
Here.
Thank you. David Mass. Dave. Let's see who's coming online here. Toby. Okay.
Here.
Dave, are you there? Okay.
Yeah.
Okay. Thank you. Ryan McNeil. Okay, Gabriela Montes. Yeah, Gabriela is not coming, right? So I gotta drop her. Danielle Nwagbu.
Here.
David Nwagbu.
Present.
Okay, Claire Bottinger.
Here.
Angela Padua. Let's see, Angela Padua. Yeah, still registered. Okay. All right. Maria Raju. Let's see, Maria Raju is still registered too. Yeah. Jennifer Ramirez. Yep, thank you, Jennifer. Noah Raymond.
Here, Professor.
Thank you. George Risk.
Here.
Shah Safi.
Here.
Natalie Santiago.
Here.
Nathan Silva. Yeah, Nathan Silva is, yeah, okay, good. Thank you, Nathan. Darnice Simon.
I'm here. Why
Okay.
is there an asterisk in the day before? I was also present.
Yeah,
date.
I called you, but you didn't answer yesterday.
I did.
Okay.
I put it in the chat.
Okay, thank you.
You're welcome.
Your code, Sobi. Code, Sobi. no. Good. Let's see here. Aidan Tadeo. Okay, you go. I don't see Aidan Tadeo. Okay, Aidan is no longer in my list. Let's put it here. Tadeo, good. Sandra Valencia. Sandra Valencia is no longer in my list either.
Prof,
Yeah.
Prof, could you hear me?
Yeah.
For Lauren.
Yeah, I can hear. Is that Lawrence?
Lawrence, I'm here. I'm sorry. Yes, Lawrence Flores.
Okay. Send me a text message or breaking up. Okay. Chat message.
Okay, thank you, Prof.
Okay.
Thank you.
Welcome. Sandra Valencia. Okay, Sandra is no longer registered. Kenny, are you there?
Yeah, I'm right here.
Okay. Robert Wall. Robert Wall. Okay, Robert's no longer. And Nolan.
Yeah, I'm
Nolan
here.
Williams.
I'm here.
You're there, Nolan?
Yeah. Can you hear me?
Yeah, I can hear. Good, thank you. Mengshu. Good, thank you. Now, let's see. Ki Pie So. So, okay, still on the waiting list. Ki Pie So. Okay, Olivia Song, are you there?
Here.
Okay, did you try to add Olivia?
Not yet.
Yeah, I believe you can add. If you need an add code, let me know. Okay.
Okay, thank you.
Sarina Lobana. Are you there, Sarina? Yeah, okay, good. So you managed to add, right, Sarina? Let me put you there in the good. And Alexis Nigret.
Here.
Okay, you managed to add, right, Alexis?
Yeah.
Okay. Okay. Nigret. Here we go. Let's see, someone is trying to come in on board. Claire. 8:56 now.
Oh, Professor, I'm here. Toby.
Who's that?
Toby.
Toby. Okay, okay, here goes. Thank you. Let's see how many students we have now. 33. Good. The numbers here, 33 matches with my attendance here in Zoom. So we're in good shape. Let's take a break. And then we start. Break till 9:15 a.m. And then after break, we start waves. After break, we start waves. Okay, we're back here. So let's start talking about a wave, right? So a wave is a very useful concept in physics. It's a very abstract concept as well. But the advantage of that is that it can be applied to several types of phenomena. That's the simplest. Let's go here to my notes here. Here you go. Waves, okay? It is a very abstract phenomenon. It's a very abstract concept. And the best way to understand it is through examples. The simple of all examples is one of them, the simple of all is the mechanical wave in a string. We can visualize it. That's why it's a very useful one. This one we can easily visualize it. There are other types of waves that we cannot visualize. But if you understand a mechanical wave in a string, you will be able to visualize those types of waves that are invisible. And so what are the types of waves that we have in there, in addition to mechanical waves? Well, we have sound waves. We cannot visualize the waves propagating in air, but we can hear it, right? Another type of wave is an electromagnetic wave. Light, for instance, light is an electromagnetic wave. You cannot see the waves of light vibrating back and forth in space, okay? Actually, it's the electric and magnetic fields that are oscillating back and forth in space, producing a wave. Okay, and when I mean electromagnetic wave, I mean not just light, I mean also radio waves. I mean also UV radiation, UV light, infrared light, X-ray, and gamma rays, etc. Microwave, we can put microwave here too. Microwave oven generate microwaves. Those are the types of electromagnetic waves that we have in there. Okay, we also have water waves, right? Water waves can be visualized as well. Here you go, let's put the water waves here as type of wave that can be visualized. Water waves. Waves that we cannot visualize, waves we cannot see, right? Slash visualize are the following. So let's talk a little bit more about that, okay? So here you go. We have transversal waves in a string. You get a string, fixed between two positions, and you can move it, not fixed between two positions, just one position here, right? You get the other end of the string, move it up and down, and you generate a wave that you can clearly see. Those waves are called transversal waves. And you can do the same in a sling. And then we have longitudinal waves in a sling. Longitudinal waves in a sling is something that propagates like that, along the length of the sling itself. And here, gravitational, you don't forget gravitational waves, right? They were just detected recently, was predicted by Einstein back in the early 1900s. And only now, 100 years later, more than 100 years later, we're able to detect gravitational waves. And we also have particle waves that I didn't mention to you, which occurs in mechanical quantum mechanics, and we are going to study it. Let me put here in in this order now. Okay, so basically waves is a disturbance in a medium. That's a good way of defining that. A wave is a disturbance in a medium. You disturb the medium and you generate a wave. But you also have waves that do not require a medium. Most waves require a medium to propagate, but not all waves require a medium to propagate. Like electromagnetic waves. Electromagnetic waves, they can propagate in vacuum. There's no medium in there. There's no matter, almost no matter in the vacuum. But electromagnetic waves do propagate. The medium in this case is the medium between quotes, right? Is the electric and magnetic field. So here you go. Here you go. Here's an example of our mechanical wave. Now you can get a rope or a string and move it up and down. In order to generate a wave, you have to have a source of vibration. You have to have a source of vibration, right? So here you go. Let's write it down. In order to create a wave, you must have a source of vibration. It doesn't matter if vibration lasts forever. It doesn't matter if vibration is just for a small amount of time. Okay. In the case of this mechanical wave, here you go. Basically, what we're doing, we have a source of vibration right in here in this left side of your string or rope. It's moving up and down. I am exaggerating this distance here, okay? I'm exaggerating on purpose so you can visualize it better. What we have here is a train of waves. The simplest wave that we have has this shape of a trigonometric function, cosine or sine. And in this specific case, the peaks here of the wave, we call it crest. Crest here, a crest here. A valley. And the point where the wave doesn't have any displacement in the y direction, we call it a node. One node here, another node here, and so on. This position that you see here is the position of equilibrium. If there is no vibration, you have a straight string right in here along the x-axis. Okay, and the distance from the position of equilibrium to the crest, we call the amplitude of the wave. By the same token that we have amplitude of vibration, right? The distance from here to the maximum displacement from equilibrium, we also have an amplitude for the wave. So let's write it down. So here you go. So relation between oscillations and waves. Okay. 1, oscillations generate a wave. Oscillations have a frequency. So the waves do a wave. Oscillations, if you have a frequency of oscillation, you are going to have a period as well. Now you should know the difference between frequency and period, right? Let's write here. What's the frequency? Frequency is number of oscillations per second. The unit for a frequency is going to be the hertz, which is equal to the inverse of a second. Okay, the 1 here represents the number of oscillations. but because we're dealing with a unit, you know, we rarely have anything that's not that's different than a 1. Okay, so the wave also has a frequency. You know, frequency is the number of oscillations per second. What about the period? Period is the inverse of a frequency. How long it takes for a full oscillation? The unit of period is the second. Okay. And what else do we have? Oscillations. And waves have an amplitude. The amplitude can be meter, depending on the type of wave. Depending on the type of wave, can be meter, but can be other things too. Can be even in pressure, okay? Unit of Pascal, depending on the type of wave. It can be in unit of electric field, can be in unit of magnetic field, and so on. Okay, in electric field is going to be Newton per Coulomb, right? Magnetic field is going to be not Gauss, but Tesla. Okay, Tesla, etc. Okay, let me here write that. And waves have a period. Oscillation and waves. And waves have a frequency. Okay. So going back here. But then waves have something that that an oscillation doesn't have. Okay. Okay, waves have velocity. Waves have a velocity. Not the velocity of this oscillation, okay? Because there are two velocities, right? There is the velocity of oscillation. There is the velocity of oscillation, right? Up and down in the case that you saw in there. And then there is the actual velocity of the wave, you know, and there is the velocity of the wave, of a wave. So going back to our drawing, you know, this wave that we are generating is moving from the left. This disturbance that we're generating are moving to the left, from the left to the right. So in this case, we're going to have two velocities. We have this vertical velocity here that changes as time goes by. And we have this other velocity here that's constant. This velocity is perpendicular to this other velocity. The velocity of oscillation is perpendicular, in this case, is perpendicular to the velocity of the wave itself. Okay? This type of wave is a transversal wave. Transversal wave because the amplitude is perpendicular to the propagation of the wave itself. Okay. What else? What wave has that oscillations do not have? Okay, waves have this wavelengths. Okay, wavelengths as well. Waves have a velocity, have a wavelength, which is the distance between peaks, between crests. Distance between crests. Okay. Yeah. So keep that in mind. Amplitude, wavelengths, velocity. velocity of the wave, not the velocity of the oscillation. You know, there is velocity of oscillation, and then there is the velocity of the wave. So what you have to do in a mathematical sense, what you have to understand in a mathematical sense is that this, you know, the position here along in the position of those points in this wave is a function, not only, you know, of the position. We go insert here, equation. For that transversal wave, you know, the vertical position of the points of the wave is going to be a function not only of the horizontal coordinate, the x coordinate, but a function of the instant of time as well. Okay, let me see if I can show you a simulation. Here you go. Yeah, I guess this one here. Oh, here you go. I have a simulation for you in Excel that you can do yourself too on your own of a wave. Okay, I put the wavelengths of the wave, I put the velocity of the wave, and as time goes by, and the position along the horizontal direction. This type of wave is called a transversal wave. Let's put a time t equal to 0. Here you go. That's how the wave looks like. This is a cosinusoidal wave. If you go here, here you go, cosine. I'm going to show you how we can mathematically model this type of wave. We're going to get there, but just as a simulation, you know, a nice illustration of how a wave behaves. I put the velocity of the wave, right? So here you go, as time goes by, here you go, this wave is moving to the right. See that? So a given point in this wave depends not only of the x coordinate, but also depends on the t, instant of time t. Here you go. This wave is propagating to the right. Okay, 9, 10, 11, and so on. Okay. If I come up with a negative speed here of the wave, okay, if I come up with a negative, let's go here, 0. What's going to happen to this wave? The wave is going to propagate to the left. See that? The model works, the mathematical model works very well. 8, and so on. If I change the amplitude from 0.3 to 0.4, okay, the wave is going to grow in amplitude. Don't forget that the range here changes, right, from 0.4 to 0.5. I can also increase the speed of the wave. Let's increase to 2, you know? Let's increase to 2. So start at 0. Here you go. So now you're going to see what's going to happen for every second. You're going to see a larger displacement. Okay, a larger displacement of the wave. Whereas if we had like minus 0.5, right? 0. Remember that? Here you go. 1. See, we had a very smaller displacement because the speed is lower than the other one. But how do he go? Here we have the wavelength as well that I can change. In this case, the wavelength is 20 meters. Let me put a time t equal to 0. Here you go. This peak goes from 0 to 20. See that? But I can change the wavelengths. Let's change to 10. Here you go. 0 to 10. Let's change to 15. How do we model something like that? Okay. Okay, waves has the following generic mathematical solution. Here's just you know, too generic for a wave. Okay, but if you want to be more specific, a more specific equation for a wave is the following. Okay. Very important to it's gonna be let's see, kx is gonna be something like kx minus vt. Okay, can be plus and minus as well. You go. Can be one is gonna propagate to the right. This one is gonna propagate to the right. And this one here is going to propagate to the left. See that? The negative sign means propagation to the right. This k that you see right in here is 2 pi over lambda. Lambda is the wavelengths. We denote lambda as the wavelengths, like that. Okay. Even better, you know, if you want to bother about those constants, you just write down. No, it's not kx plus dt, it's x plus dt. You go. You just write down like that. So this function that you see here for a wave has a more specific relation. Can be x, you know, a function of x minus vt. That function that you saw in the simulation, the function that you saw in the simulation, you know, has the following format, mathematical format. It's going to be cosine. Okay, and now I can put that constant that I mentioned to you. Here you go, 2 pi over lambda. Here you go. But it can be a sine as well, depending on the wave. This wave propagates to the right. To the right. This other wave, you know, let's put here right propagating. Wave that propagates to the right. Wave that propagates to the left. Okay. If you want to be more specific about the function, you have to define what the function is. What you see in that simulation is a cosine type of wave. And all you have propagates to the left. Remember, the plus sign means negative propagation. Negative sign means positive propagation. It's possible to prove that mathematically. We've seen that, by the way, we've seen that for the first time. Can I get some feedback from you so I know how much you know about that? I presume that some of you have already seen that in your physics course elsewhere, right? So let me see. Let me go through my list here of attendance. I'm going to ask you, Toby, are you seeing that for the first time? Is Toby there? Okay, I haven't heard from Toby, so let me put a question mark here. Harun, are you seeing that for the first time in this physics course, in a undergraduate physics course? Are you there, Harun? Wow, oh man, let me put that question mark here. Musa, are you there? Man, let's see. Zachary, are you there, Zachary? Mhm. Wow. Mm.
Professor, I'm here.
Yeah. Okay. Have you seen
Haru.
waves before?
Waves? I think, yeah, in chemistry.
Oh, in chemistry. Okay. This type of
Yeah, Chem
but what
101.
about this type of mathematical treatment? Have you ever seen? Did they teach this type of mathematical treatment in chemistry?
No, they just had a formula, like a simpler one.
Okay. Okay. In chemistry. Okay, but you didn't see that in your undergraduate physics course, right?
No.
Okay. Elena, have you seen that before?
Yes, when I did AP Physics, we did like a little bit.
Oh, AP Physics, right? But AP Physics is calculus based, right?
Yes.
Okay, it's calculus based. Okay. So, but what about at the undergraduate level? Did you, at your school, did you see that?
I don't think so.
Yeah, you don't. Okay, you saw that at high school. Okay. Luis, are you there? Luis Crystal? I don't think he's there. Okay. Robert, have you seen that, Robert? Robert, okay. Doesn't look like Robert is there. Pedro Flores, have you seen that, Pedro? You haven't, right? Because you took physics with me. Huh. I can't hear you, Pedro. Okay, so let me get Olivia. Have you seen that before, Olivia? Let me get here randomly.
I have in other classes.
Okay, in other classes. Okay, it was in physics or
Yeah, just in
undergraduate
other physics classes in college.
Okay, undergraduate physics. Undergraduate physics. Okay, thank you. Okay, so let's continue here with the topic. Right, here we go. Here's the simulation, and the equation that we have is something like that. Don't forget you have also the amplitude right here. Here's the amplitude, here's the wavelengths, and here's the velocity of the wave. And by the way, it is possible to prove that there is a relationship between the velocity, the wavelength, and the frequency. Okay, so how do you do that? There's a very simple formula. There's a generic formula, not just velocity, but speed, right? The speed of any wave, okay, any wave. The generic equation for the speed of any wave, it's not velocity, but the speed, generic equation for the speed of any wave is, that's very easy to remember, is the wavelengths divided by the period. Can you remember that? So the period is already implicit right in here in the speed of the wave, which can be rewritten as lambda times frequency. Lambda times frequency. Can you remember that? Okay. So distance, right? Time. Distance time. Delta x over delta t. Okay. So because of that, these both equations can be rewritten if we expand it, right? If we expand it, that's another way of writing this equation would be 2 pi over lambda x, 2 pi over lambda x, right? By the way, 2 pi over lambda, we call it the k. The lambda here cancels the other lambda, and we have this relation. And 2 pi f has a name too, right? You saw 2 pi f before. What's 2 pi f? 2 pi f is omega. Omega. Okay, that's another way of writing the wave. prefer this format here. I prefer this format here. Here you go. Oh, this one right here. Because it has, the x minus vt that we all know. Vt has units for x, right? So kx minus omega t. K is called the wave number in the above equation. K is called the wave number. But the basic quantities for wave are, again, 1, amplitude A. 2, wavelengths lambda. And what else? You can take period. Everything else, period t. Okay. And then, those are the 3 independent parameters of a wave. You can also call the variables, right? X and t. X is another parameter. It's a variable x. And the variable t. Taking of the frequency, just remember frequency is the inverse of period, right? And we also have the speed that depend on the main parameters lambda and period, like that. So there are, among the parameters, you have to memorize only 3. Everything else is dependent on the rest. And then we also have, we have the wave number, right? Wave number k equal to pi. Let's see, let's get that. 2 pi over lambda. Here you go. That's this one here, okay. So here go. At time t equal to 0, we have a given function, right? It's going to be a cosine function. So let's take a look at our, here time t equal to 0. Let me go back to my positive velocity, positive speed here, not velocity, speed, right? That's how the wave looks like at time t equal to 0. And here's the dependence that I already told you. We can prove that if the wave propagates from the left to the right, cosinusoidal, okay? And okay, here's the proof of, how why the positive means backward propagating wave and negative means forward propagating wave. I'm going to skip that. You can look at by yourself, it's easier for you to memorize that negative means forward, positive means backwards. It's easier to memorize, but here's the, the proof, the exact mathematical proof. Just all you have to do is to change your referentials. That's exactly what I'm doing here. Change the referentials from the original referential to a referential that moves with the wave itself. Okay, and in the process, I I proved that the negative means forward propagation, the positive means backward propagation. Okay, so that's this type of waves, sinusoidal and cosinusoidal waves, we call a plane wave. Okay, that's the most important type of wave that we have. Plane waves are waves that have a circular function, right? Sine or cosine have that are written in terms of this circular function, sine or cosine, circular function, sine or cosine. But like I said, there are other types of waves too. You can have, you know, in addition to those waves, you can have, for instance, we can also have triangular waves. Okay, you can have square waves. You can have exponential waves, okay, and so on. Each of those waves can be written in with an argument that's the same that you saw in there, etc. Okay. You know, so let's see. Let me give you an example of a triangular wave. Okay, triangular wave. We go. Can be something like that. We can even, you know, put an amplitude in there as well. Right? If I, you know, this, you know, in this specific case, I'm going to illustrate here for you as well, and simulate here. Here you go. Going here to my Excel, right? Let's okay, linear, more like a linear wave. What I'm doing here, what I'm going to do here is x minus b times t. Okay, and I gotta get, yeah, I gotta get another $sign here. Clicker, and you know, I'm not gonna go very far, otherwise the wave is gonna look too big, you know. Here you go. I'm gonna plot this one here. Insert. Okay, here you go. And now if I go ahead and start the simulation, look what happens. The wave starts propagating. Oh, let's see. Wait a minute. This one looks like this one is yeah, good. Yeah, this one it has a minus sign here. It's propagating forward. Let me put here y linear. Okay, so 0, right? You go 1, 2. See, the wave is moving from the left to the right. Ideally, this, you know, this thing here is supposed to be. Let's see if I can get it. Let's see. Yeah, well, let's leave this way. Let's leave this way. Okay, I'm going to, let me see, I can do that in PowerPoint as well. Okay. Okay, what do you have here? Is a pulse. If you're going to, please, Okay, I gotta do that from scratch. That's easier. Okay, I'm gonna use this X and Y axis for this one. Okay, here you go. Linear wave. So we can illustrate that in this way. Here you go. A triangular wave is gonna be, pieces of linear function. Just like we have repetitive linear functions. Okay. So if you want to make it to propagate, you can illustrate like that. Okay. In this manner. We can even, put a little bit here to the left. Okay, and here you go. In this way, this type of function, can be written down in the following way. Can be written down like that. Here you go. Must have a negative, a function of x, and a function of t. We also can have, exponential waves. Exponential waves, in which they are going to look like the following. Here you go. Exponential x minus vt. Okay, and so on. There. Oh, and by the way, this guy here is supposed to have a k here in front. So the exponent of the exponential is unitless, right? 2 pi over lambda x minus vt. It was me who saw it. Okay, thank you. $9.58. Any questions about that? Okay, so here you go. Here is the wave number, angular frequency. Here you go, the building blocks of a wave. You don't have to memorize a bunch of those parameters, right? All you have to memorize are those 3 parameters. Everything else that comes from those 3 parameters are additional, are the, let's say, secondary definitions of the wave. Well, in addition, so here you go. Let's go back now. Let's do our actual math, right? Now, here you go. We're going to go back to our sinusoidal wave. And yeah, let's get this one right in here. Go. So a wave has 2 speeds. Okay, a wave has 2 speeds. I'm going to put it here, kx minus vt, the speed of the wave, and you also have the vertical velocity of the wave, of the points of the wave. How do we find that out? Okay, so that's all you have to do, is to differentiate that. And let's not forget, this is we're talking about one-dimensional waves. partial. Let's see, no, partial. Let's go here, dy. Partial derivative right in here. Okay. We can also have vertical velocity of the point of the wave. And then when we take the derivative of this, we get kV negative. We're doing for the cosine type of wave, right? Take the derivative of that, AKV. So if you look at my sinusoidal wave, here you go. All those points are moving back and forth, okay, up and down. So what we saw in that equation is the equation for the vertical speed of those points, okay, which is nothing but the velocity of oscillation, right? That we saw for our harmonic oscillator. What else you have to know? Here you go. I did all the derivations here. Here you go. I put that omega t in this case, which is the same that you had before, and the maximum velocity. Here you go. The maximum velocity along the vertical direction is going to be given. Here you go. Is going to be given, and I'm going to put the magnitude as well. Here you go. AKV. Here you go. Amplitude, K, which is what is no S supposed to be here. Here you go. This guy is 2 pi over lambda. Right, and the velocity again can be here written as what? Lambda over period. Okay, lambda cancel out with lambda. Lambda here cancel out with lambda. We end up having a 1 here. The inverse of the period is going to be the frequency, and 2 pi f is what? The angular frequency. Go, A omega. Is that what we have there? Let's take a look. Here we go. Yeah, A omega. The maximum velocity along the vertical direction. We can get the acceleration as well, just by taking the second derivative of the position in the vertical direction, right? So it's 2 different velocities. Here you go. We end up being 2 different accelerations as well. Let's take a look at the acceleration of the points in the vertical direction. Here you go. It's going to be A, Y, second derivative. Okay. So take the derivative here. Sine becomes cosine. And when you take the partial derivative of this other one, we get minus kv. Here you go. K square v square. Okay. That's the type of games that we can play with those equations. And so it's already 10:06 right now. Let's take a little break again. So you can get, stretch a little bit, take something to get something to drink or eat. And let's do
Professor,
yeah, go ahead.
I don't know if you were calling on me earlier, but I just stepped away to grab breakfast.
Yeah, who is that?
Pedro.
Oh, okay, yeah. Oh, yeah, I
Yeah.
called you a few minutes ago. Yeah.
Yeah, sorry, I was grabbing breakfast.
Okay, thank you for. Okay, break to. Let's do 10 minutes. 10 minutes break. Break to 10:16 a.m. Let's do this way. Just 10 minutes this time, and then we go until 10:30, and then we go until 11:30. Any questions before we go into the break? Okay, see you shortly. Okay, so here you go. So we are back here. And let's just summarize what we have done so far. Summarize what we have done so far. Okay, so here you go. We're working with waves. Well, okay, what's the genetic mathematical function of a wave? Okay, so the genetic mathematical function of a wave is what you saw before. Here you go. Something like that. We can put, you go, like that. Building blocks of a wave. Building blocks of a wave. What are those? So we have wavelengths. We have the period. Right, and there is one more, it's the amplitude. Okay. A wave has a speed in its direction of propagation. Which is constant, by the way, which is constant. And you can have all sorts of waves. You can have planar waves, types of waves. Planar waves, sine and cosine. Have triangular waves. We can have square waves, etc. You can write exponential waves as well. All those waves should repeat themselves along the x-axis. Okay. What I want to do now is to introduce you to the wave equation. Okay, this is a differential, it's a very important equation. This is a partial differential equation. Partial differential equation. defines a wave. Okay, which it's possible to derive it mathematically, but I'm not gonna do that because it's lots of work. Okay, so what you have to remember, the wave equation is a partial differential equation, a second order partial differential equation, and can be written in the following way. Here you go. It involves both a partial differential in time. It relates, the y coordinate of the wave. And a partial differential in space. Will be something like that. Actually, what you end up having here is a proportionality constant, okay? Can you memorize that? The key now is to find out, the proportional is a proportionality sign. The key now is to find out what would be the constant that goes there inside. Okay, let's say I'm gonna put a C here. Okay, so here you go. So here you go. I'm gonna put the proportionality sign here. Go back there. Step by step. Just remember, the wave equation involves second order partial differentials. The second order partial differentials is going to be in terms of the variable, right? That the wave depends that d2y dt2 and d2y dx2. Those two partial differentials are related to one another by a constant, by the way. Okay, and now the question is what is this constant here that we are talking about, right? Well, it's very easy to find that out what this constant is going to be just by doing some dimensional analysis. Okay, so remember that what you have here on the right side, the dimension. That's why it's so important to learn dimensional analysis. That's why we teach dimensional analysis in physics, right? So it can be used as a tool to have an idea of how an equation is going to look like. In the case of this, of this partial derivative, the unit of this partial derivative is going to be in terms of meters per second square, right? Here you go, the unit of y divided by the unit of t square, right? Whereas the second order partial differential equation has a unit that's going to be meter divided by meter square. This is a technique that we use to find out what's going to fit right in here. Okay. And this constant. So this constant, let's see. So based on this equation that we have right here, right? We can write this constant in this way. Here you go. And the unit of this constant is going to be the unit of the top term divided by the unit of the term in the denominator. Okay, so the top term has this unit. And I'm gonna do another step here to simplify, right? I'm gonna do that, inverse of meter. Okay, and look what we get. We get that this constant has the unit of the square of the unit of speed, meter square per second square. Okay. Based on this simple analysis, we can state that this constant should be, in reality, a velocity square. Okay. So, and if you go through a speed square, even better, a speed square, not velocity, but speed square, right? And if you go through the tail derivation of the wave equation, you do get something like that. Let's make sure everything is right. No? We're doing just a dimensional analysis to figure out how the wave equation is going to look like. Go. And here you go. We have the same equation right here, right? Written in a different format. We usually write with the other partial derivative on the left side. You go. That should be x2 t2. Okay, and 1 divided by, here you go. Oh, like that. What can we do? Can you remember that? That's a very important differential equation to remember. Many waves obey this differential equation here. The wave in a string, for instance, is solution to this partial differential equation. And that's what for one-dimensional, 1D partial differential equation for a wave. Okay. For a 2D, you have to put another, and we do have two-dimensional waves out there. We end up having something like that as well. And then let's see, I can put, shouldn't be Y in this case, should be something else like Z, right? And so on. So what I want to do now, demonstrate, prove that the function start with the negative one. Satisfies the wave equation. A very good exercise to make. I'm going to give you some time for you to do that. I'll give you like 3 minutes to set that up. The one-dimensional wave equation, the 1D wave equation. satisfies now is solution, right? Is solution to the 1D wave equation. So see if you can do that on your own. A very good exercise to practice your mathematical skills and your knowledge of as well of waves. You have to be using this equation right in here. The 1D wave equation. Let me take out. Prove, there you go, prove that the function again, try it on your own. Stop recording. How are you doing there? Keep me posted, you know. I'm going to go even further than that. I'm going to see, you know, I'm going to say like the functions, you know, this one and this other one. Because those two are different, I'm going to name the second one a y prime. Prove that the functions are solutions, right? The 1D wave equation. Anybody's there needs any help before we move forward? 2 minutes already. I usually give my students like 3 minutes to set up everything before I do any solution for that. Minutes. Okay, who let's do it together now. So here you go. We have derivatives in x and we have derivatives in time. What we have to do is to differentiate this equation here in terms of x and t, and see if those differentials satisfy this equation, and then repeats for this other function that's slightly different from the first one, right? So what we do is start with the x. The first derivative of y with respect to x. Oops. Right, it's like that. Here you go. Oh. Okay, here you go. Here you go. Like that. We're going to okay. So what we do here, we define x minus dt equal to a u function. That's what the little trick that we use. Okay. And when we do something like that, the f function becomes a function of a single variable f. But let's not forget that this u function, that's now, is also a function of x and t. This new variable, right? U is a function of x and t. So when we take the partial derivative of f with respect to x, we apply the chain rule. It is, you have to do like that, total derivative of f with respect to u, right? And a partial derivative of u with respect to x. Here you go. Going back to the definition of u, we find out that du dx is going to be 1, right? And this total derivative can be here written as f prime in short for df du is a total derivative, right? I'm gonna put it in a simplified format. We did only the first derivative. Let's do the second derivative now. Second derivative of y, partial derivative of y with respect to x. Okay, so here we go. And go parentheses, like that. Okay, we found out that this term here you go, let's repeat it here. Let me erase the rest. We found out that this term here is the f du. Okay. Which, by the way, is a function. Okay. Which is also a function of x and t. Go. Let's put that right in here. Okay, so we have to go the next step here. Let's here we go. Solution is right. Let's see. Mathematically. Go. That. You know, I call it G of U, right? It's better. Instead of calling F prime, right? We call it that G of U to simplify the notation. Okay, and then here you go. That's a function of U. And then we repeat what we did before. Adopt the chain rule. The du. That's the total derivative. Du dx. Here you go. Du dx is going to be 1. Okay. And, you know, dg du, I can write that down as g prime. And give it a name for this function as well. Oops. Let's take a look at the functional name that I gave it. Let's see here. Well, I didn't give any name to that. I just kept it as dg, which is the second derivative of f. Total derivative of f. Second total derivative of f. We didn't finish that yet. Now we have to repeat for the partial derivative of t. Okay, like that. We go. Oh, change it to t. Okay, here you go. T. Okay, and then you have to take this derivative now that's going to be different from the other one. It's going to be minus v. Okay, minus v. Minus v. Minus v, the function that I call g times g. Then we have to take that. So let's make sure that I got everything right here. Go. dy dt, right? Take the du dt, that's good. Okay. And I gotta repeat for the second derivative. Okay. Here is going to be minus, oops. I'm gonna put the minus here outside because it's a constant. Okay, minus v. Let's see here. We have to have dt. See here, dt, dt, yeah, dt. Okay. Then gotta change to t. as well. And du dt again is going to be minus v. So we're going to have minus v multiplied twice. Here you go. Okay, and that reduces to, oops, here you go, let's reduce this to v squared du dt v squared d2 f du2, or v squared prime to prime. Okay, so that's now what we're going to do. We're going to substitute each of those partial derivatives into this equation. Okay, so here you go. I'm gonna repeat it. Go. Right, the partial of y, second order of partial of y dt2. We go, it's gonna be like that, and look what we get. We get that v squared cancels out with v squared, and we prove that this is equal to this, right? So we prove that f of x minus bt is solution to the wave equation. That's the most generic procedure that we have, because we are adopting a solution that is for any wave. You can repeat for x, f of x plus vt. And then you can do that also for a planar wave. Okay, so let's do that. Now that you have the recipe, try to do that yourself for a planar wave, the generic recipe. Here you go. Example, you know, instead of exercise, let's call it example. Example. Here you go. Example. Prove that the function cosine, you know, let's see, k x, okay. The functions. Oh, by the way, should have a amplitude here. Amplitude are solutions to the one-dimensional wave equation. Okay, and then I'm gonna write that down, solution here. Again, I'm gonna give you some time to work on that. You can follow the recipe that I had here for the most generic case. Okay. I'll give you 3 minutes. Think about that. This one is easier than the previous one. The previous one that we did. 1 minute and a half. Two minutes and a half. How are you doing there? Let me get some feedback for any one of you. Okay, 3 minutes. Let's not forget, you know, this one here is a constant, this one here is a constant, right? Notice that for the previous example, I didn't do the backward propagating wave, right? I want you to do that on your own. But the procedure is the same. Okay, so here we go. Let me see here. Yeah, okay, good. So solution, just like we did before. Here you go. Here's my recipe. Right, here you go. But even copy and paste in there. So you can follow. Here you go. It's gonna be easier now because it's not just a generic function that we do not know the format. Okay. Like that. In this case, we don't even have to define this because we already know the functional format, the exact functional format. Right, so here you go. So what we do here, we're gonna copy that. We take the derivative of that function becomes, the function becomes minus sine. And then we have to worry about differentiating the argument of the function. Okay. Does it fit there? Let's see if it's gonna fit in this line. Okay, so this derivative here is gonna be 0, right? So I don't have to worry about that. K is a constant. You know what? Let's see. I don't want to skip any steps here. Let's see. Go like that. Yeah. Okay. Like that. And finally, we go K. First derivative. First derivative. I'm not gonna need that. That U function was important to be introduced just because we are dealing with a genetic function f. I don't need that anymore, but now I'm gonna need this one. Okay, dy dx is going to be, let's say, dy dx is gonna be this one here. I don't need that. I don't need the rest anymore. The constants go outside. Okay. We go. Sine becomes cosine. Okay, and we have to differentiate. Just the argument. When you differentiate just the argument, what is left is just the k, right? And that's our second derivative with respect, partial derivative with respect to x. And then we repeat for time, for t. Let's go get it, this guy. Okay. That's what we get here. Next step. Maybe, you know what? Maybe I'm gonna just copy this one here. Yeah, let's copy this one here. And I replace, you know, I replace the partial derivative with x with t. Here you go. Since I have everything ready already. You go to t right in here, right? Let's see. Yeah. Yeah. This one disappear. Oh, no, this one disappear. Negative, oops. Negative v. This negative cancel out with this negative. Kv are constants. Oh, let's see, it's supposed to be t. Here you go. Fine, let's see, yeah. Vt, vk, sine, okay, and then we have to go the next step now. The second derivative. I got everything that I need for the first derivative. Hopefully I didn't make any mistakes. Let's see. Yeah, now let's go for the second derivative. in time. Second derivative in time. Let's see here. That's the one I want, not the other. Let's do it again. Second derivative in time. Go. I'm going to, oh, not that I want to go. This one like that. Let's see here. Like that. Okay. I have placed that here, right in here. Any questions so far? AVK can be taken out. AVK and go. This sign becomes cosine. There is no negative there. And we are left with differentiating with respect to the argument. This term on X disappear. Right, minus VTK. Minus V. Let's see, put it here. K combined with this other K. Okay, V squared. Let's see if we're getting there. Right? Hopefully I didn't make any mistakes, right? Did you see any mistake that I made here? Okay, this dt disappeared. Let's see. I'm suspecting that I made a mistake somewhere because I have a negative here. You don't have a negative there. Let's see. Anybody? Oh, no, I have a negative here. Okay, good. So yeah, seems that we're in good shape. Go. And now, okay. Let's summarize what I have here. Here we go. That's one, that's the other. That's one, that's the other. Okay. Substitute this one right here. Right. You go. 1105. You go right here. Here you go. Substitute this one right in here. Are you gonna get the right solution or not? Let's see. Oh, that go another step here. Negative goes outside. This guy gonna go upstairs. I don't need parentheses anymore. Okay, that's what I'm doing is this part here. V square cancel with V square. And we can continue our derivation. Here we go. That's the step I must take it out, right? What we have here is d2y dx2, right in here. What you have here is d2y dt2 divided by v squared. Okay, here is the left term of the differential of the equation. Here is the right term of this differential equation. So here you go. Negative cancel is negative. AK square cancel is AK square. And here you go. We have that cosine kx minus vt is equal to cosine kx minus vt. Okay? So that's what the QERAT demonstrator, right? QED. So we proved that the planar wave is solution to the wave equation. And you can do that for the other things, okay? There is one more that I want to do. Here you go. Here you go. That's my notes. My notes, right? So another exercise. You can repeat that for the backward propagating wave. Okay, this one's an interesting problem, right? So the question is does this equation satisfy the wave equation or not? Okay, that's, so I'm gonna get there to my notes. And another example, that would be example 2, right? Example 3, determine whether, C is square root, let's see, is square root, yeah. Oops. Minus square root of the t. This one here, C is a constant, an appropriate constant. Determine whether this equation, the equation is solution to the 1D wave equation. Okay. Let's do that one more. We have another 20 minutes before we go to our lunch break. I'll give you 3 minutes. Think about that. or not. Okay, or not. It's the same recipe that you have to follow, right? The wave equation, here you go. Two minutes and 10 seconds. Oh, 3 minutes already. More than 3 minutes. Let's do that together. Okay, so for the first thing that you have to do, is to see whether this guy here has that functional format that I mentioned to you before. Does it have that functional format x minus vt or not? Does it have? Now, does it have this format here? It looks like it has, right? But in reality, you don't, because you have separate terms here. You have separate terms here. If you were, if you had something like that, yeah. Let's see. No. Then that might have been a solution to the wave equation. That would have been a solution, but let's prove that mathematically anyway. Okay, you're gonna see. So here you go. We go ahead. Place it here. C is a constant, can be taken out of the derivative. Okay, I'm going to do another step here. This one is not going to contribute to the derivative. Okay, and we get we're gonna get what? X to the minus half, x to the minus half, which is the inverse of the square root. You got inverse of the square root, like that. And we're gonna get the other derivative here. Okay, second derivative now. There you go. We take out the constants. Take the constants out of the I'm gonna put this, x to the minus half here. That's easier to differentiate, right? Makes it easier to differentiate. I don't need that anymore. Minus half. Okay. Then this guy is gonna be minus 1. Should be minus 3/2. 1.5 is 3/2. That's the second derivative. Because see, equal. And then we repeat for dy dt. We got dy dt here. And let's see if it satisfies the wave equation or not. There you go. The C goes outside. Yeah. In the next step, the first term doesn't show up. Okay. Here you go. Go like that. The square root of b is a constant, so it can be taken out of the differential, and we are left with this derivative. Okay, I don't need that, right? Let's take this one out. And we take the derivative of this square root. 1 and, t to minus half. Oops, t to minus half. Here you go. Okay. I didn't make any mistakes, right? Let's see. This negative comes from this term. this term doesn't contribute to the derivative, to the partial derivative. It looks like I have everything right. Now let's take the second derivative now. And let's, after taking the second derivative, we try to figure out that it's satisfied, whether it satisfies the wave equation or not. Here you go. Okay, here you go. Okay. Half. Okay, here you go. One more. Yeah. We're gonna have another half here, is a negative half. And then we end up with -3/2 for this t. Negative cancels with negative. Yeah. And that's what we get for our second derivative. Let's put them side by side so we can look closely at them. Here you go. Like I said, that's all assuming that I didn't make any mistakes. I'm doing those things on the fly, even though I did several times in the past. Let's see. We have this second derivative has a negative. Okay, has a negative because of that. Okay, so it looks like we got it right. Let's see if it satisfies the equation or not, the wave equation or not. Well, maybe you have noticed that it doesn't satisfy because I already told you that it doesn't have the proper functional form, right? Even though it looks like the functional form, it is not. So we'll prove, we're going to prove that whatever is in the left is not whatever is in the right. Okay, so here goes. This 1/4 cancels out, the C cancels out, but the negative sign doesn't cancel out. Okay. And definitely this thing here is not equal to that. That's different. So let's put that here. It's different. So much that we have one variable here, one independent variable here, and another independent variable here. Okay, so the equation, the function, not the equation, the function does not satisfy the wave equation, the PD of the wave equation. Does not satisfy the PD of the wave. Okay. So here we go. Let me put a one more step, right? 1/4 C. Okay. Like that. Okay. The above equality is not true. Or okay. Consequently, the function does not satisfy the wave equation. It's 11:26 right now. Any questions about that? Okay, the question. Okay, thank you, Pedro. So yeah, we can have our lunch break right now. We will meet again at 12 noon. At 12 noon, I'm gonna upload your data for the lab, and I'll take attendance again. Okay, we're all gonna work together with that data that we have, and I talk to you in 30 minutes, in 33 minutes. Okay, see you at 12 noon. Yes, I will. Just hang in there. Yeah, I'm gonna upload that to your group folder. I'm going to upload the data to your group folder. Okay, Alex. Any more questions? Let's stop sharing here. I'm gonna turn off my video and mute. Yes. Yes. If you see any different, please let me know. Fine. Oh, by the way, the notes. Interesting. Okay, I'm back here. More coming on board here. So what we're going to do is the simple pendulum, and let me do my due diligence here. What most likely what you're going, most of you what you are going to see today is you haven't seen before. Okay. Here you go. Let me go to and just start uploading the data that you're going to use. Go to Drive, and more people coming on board. 27, 28 students so far. Share folder, okay. Wiley plus setup, okay. So let's go to group folder, and we have 8 groups so far. And more students, Crystal. Okay, here you go. Lab. Raw data folder. Okay, so let me make sure everything is in the proper format here before I upload lab 9. Shouldn't be lab 9. Okay. Okay. Okay, so we go. We might need 2 meetings for this first lab, not because the lab is long, but because there are some concepts that most of you still don't might not have seen in your undergraduate course that I might want to cover next time. Okay, so here you go. I'm uploading P39 L01 spreadsheet. Okay, group 1, group 2, group 3, group 4. Each group is supposed to have some different data sets there. Okay, George is coming here on board. I presume you can hear me. You all can hear me, right?
Yes, Professor, I believe so.
Okay, thank you.
The
Yeah.
sound's a little low.
Low? Huh? Really? Is everybody's having this problem, or?
No,
Not
I can
me.
hear you fine.
Send me a chat message so you don't have a, so we have it documented and in writing, and we don't have overlaps, right, between different students, please. So let's go here. P39. Let me start sharing this screen. Can I improve my volume here? Try to increase your volume in there. Maybe, let's see. I don't think I can do anything here on my side. All I can do is to increase my speaker. I do not know if there is a way I can control my mic, the volume of my mic. Okay, so theory behind the experiment, right? So let me see if I have P39 illustrations. Is that the one? Okay. Okay, so yeah, so let's take a look here at this setup. I'm going to hide the grid lines. I don't like the grid lines appearing there. I don't think it looks nice. When we perform the experiment, we attach a small mass at the end of a string. The mass must be small compared to the length of the string for the mass to behave like a point particle. And by small, I mean, the largest dimension of the mass must be 10 times less than the length of the string, okay? So here you go, that's for the mass to behave like a point particle, right? It must be, it must be much smaller compared to the string itself. And the way
Professor,
yeah,
are you sharing your screen? Because we can't see anything.
can I see it? Okay, I'm sorry. Thank you for letting me know. Let's see. I thought I was sharing it. Here you go. Now I'm sharing, right? Good.
Yes, we can see it now.
Okay, good. So that's so you have this, this is small object, and by small I mean its largest dimension must be 10 times less than the string, the length of the string. If you have something like that, this object is going to behave like a point particle, and your formulas are going to work pretty well. Okay, so here you go. I'm gonna get, let's say, this sphere here has a diameter d. There you go. Here you go, diameter d. I'm going to erase those forces for now. I'll keep the mass, I'll keep the lengths, and by the way, this diameter d must be less than L divided by 10 approximately. Or for the mass to behave like a point particle. Let me take this one out too. We don't need that. And the way we perform the experiment, we take the mass out of equilibrium. We have a very simple experiment you can do there at home. Can get a little stone, pebble, whatever. Don't get something. Don't get a fork, right? Because the fork is too long. Attached to a string, displace it from the vertical. The initial velocity is going to be 0 because you're going to release the mass, and the initial angular position is going to be an angle there. We recommend that it can be an angle less than 10 degrees, but as you saw before, you can go all the way up to 30 degrees and still get a very small error. Okay, and so you take it out from the position of equilibrium, release the mass, wait for the mass to complete a full oscillation. What I usually tell my students is that we first do a countdown. Okay, I don't want to start counting the number of oscillations. We're going to count the number of oscillations. So we go ahead, take it out, release, and then you start a countdown. 5, 4, 3. Don't start the timer yet. 2, 1, 0. Okay, count down just like we do with rockets. When you get to 0, you start your timer and then continue counting. 1, 2. You're going to count like if you take a look at your 10 oscillations. Summer file. Let's see. Go ahead, download your. Here you go, raw data. Here you go. Take a look. Here's the data set of group number 1. Okay. Data set of group number 1. And okay. The average, yeah, it's 10 oscillations. We count 10 oscillations. And then you log 10 oscillations here for T1, 10 oscillations here, 42, 10 oscillations here, 43, okay? We perform this is 3 times to get good statistical values. What we have here in the L, we have the length of the string. Not the length of the string, sorry, it's the length from the point of contact of the string until the center of mass of your object. But again, you know, if your mass is small enough, it's okay to log the length of the string because, you know, your mass is going to be so small compared to the string that you're going to incur in a very small error. Okay, so let's get here my lab notes. Here you go. Simple harmonic motion, theory behind this experiment. I did the derivation for in the classroom. Polar coordinate system is a more convenient coordinate system for this problem, right? For the case of the Cartesian coordinate system, the X and Y position changes with time. Whereas in the polar coordinate system, only the theta, only the angle changes with time. That's the theory behind that. When we solve that second order differential equation, we get this variation in the angle. Here is the theta naught is our amplitude, the amplitude of your angle, you know, that's determined by this initial angle right in here. And here you go. The period of oscillation or the angular frequency of oscillation, the frequency of oscillation, they all depend on G and L, on G and L. If you do this experiment in real time, we cannot control G easily. No, we cannot control G easily, but we can control L easily just by adjusting the length of the string, right? It's possible to control G, but it requires you being flying an airplane or even going to space, right? Or you can have a centrifuge to adjust the G, okay? People that are JPL, they have a really nice device that they show during their open houses. You can see what happens to a pendulum whenever you have the pendulum in free fall. Have you ever, anybody has seen that? I went to those open house of the JPL. I want to build something like that. They really did a really good job, you know? It's a little drop tower, 2 meter high, and they put a camera and a pendulum there inside. The camera is free falling with the pendulum, right? And it takes snapshots of the pendulum while the pendulum in a little house, wood house, is free falling in front of you. Anybody has seen that? It's really cool, you know. I want to build one of those. But we are not controlling G. We are controlling L. Okay. G can be controlled, for instance, on an airplane. You can simulate high G levels and low G levels inside an airplane for a very small amount of time, just like those JPL scientists were demonstrating with their drop tower. We're doing their drop tower, okay? But we don't do, like I said, we don't do that in the classroom. Okay, the period is of the pendulum is given by this formula here that we derived in the classroom, 2 pi square root of L over G. So when we perform the experiment, we should verify this type of relation for the period. Okay. So you determined already, right? The period of 10 oscillations. But let's see, before we go forward, did everybody manage to download the spreadsheet that I put there in their group folder?
Yes.
Yes? Let's see. Let me go.
Yeah.
You never seen that, Nolan? Okay. Okay. So let's go one by one here. I'm gonna go through the attendance, okay? And then I'll ask you and attendance roster. Let's see. Group today is the 15th. Here you go, Jumai. Is Jumai here? No, okay, and Brian Spino. Are you there, Brian? He was here last time, but I don't see here. Okay. Next is Lawrence Flores. Are you there, Lawrence? Yeah, I don't see Lawrence here in the list. Gabriela Montes, she wasn't at the lecture, right? Gabriela, are you there? Nope. Angela Padua. Angela Padua, so he go. Angela, no. Maria Raju. I don't see Maria in the list here either. And okay, Toby, are you there, Toby? Remember, you gotta be even though you're logged into the class, you're supposed to be interacting with me. Okay, so I'm going to, if I don't hear from you, if I don't see any messages from you, then in the chat box I'm gonna put a star right here. I can see Toby's name here, but he apparently walked away from his computer. Okay, Pedro, are you there?
Yeah, I'm here. I'm here.
Okay, good. Pedro, did you download the spreadsheet that I uploaded there to your group folder?
Yes, I did download it already.
Okay, so I'm gonna put here spreadsheet. And yes, if you're in touch with Toby, please tell him to come back to the computer, right? Since he's in your group. And I'm gonna ask you too, if you have seen that JPL, you have ever been at the open house, JPL open house. And if you saw that setup that has this little drop, we call that a drop tower. Okay, NASA has those things, not the 2-meter drop towers, but much higher drop towers. NASA and other space agencies, they use those things for doing microgravity experiments, short microgravity experiments. Have you seen that, Pedro? Have you seen those?
No, I've never been at the open house.
Oh, too bad. You gotta go one day. Never been at the open house there, Jacob. Should make sure you go there before you die, huh?
Yeah, for sure.
Before you die, make sure.
Before I die.
I like to tell my students that before I die, I want to go skydive. I'm still too chicken to do that. I haven't done that yet. I just had done it indoor skydiving, but never jumping out from an airplane. I have flown airplanes, but never skydiving, from an airplane. Kenny, are you there, Kenny?
Yeah, I'm here.
Okay, so did you download the spreadsheet, Kenny?
Yeah.
Okay, have you been at the open house, the JPL open house?
No, but I want to go.
Yeah, make sure you go. Every now and then they have one of those, and look for the little drop tower. Okay.
All right.
Demonstration of the little drop tower with the pendulum and other things too. Nolan Williams.
Yeah, I'm here.
Okay, good. Did you download their spreadsheet, Nolan?
Yeah, I have that too.
Good. Have you been at JPL open house?
No, I've never been.
Yeah, okay. Yeah, make sure you, just like I told Pedro, right? Make sure you go before you die. Before you depart this world.
Professor?
Yeah, with that?
Toby.
Oh, Toby, okay, good, Toby. Thank you. So did you get your spreadsheet, Toby?
Yeah.
Okay, have you been at JPL open house before?
No.
Yeah, okay. So might be a good thing to get a bunch of people going there one day. You gotta monitor when they have those open house. They don't have that all the time. Harum, are you there?
Yeah.
Okay, spreadsheet. You get the spreadsheet?
Yeah.
JPL open house?
No.
No, okay.
Also,
Okay.
I have a question about the spreadsheet. Do we just do like exactly what we did in the previous class, like in 38? We just fill out like the graphs and the trend line and all this stuff. We just fill everything in.
That's right. That's right. And not only you do that, and you have also to understand how the experiment is performed. Okay. You have I am considering, by the way, folks, I am considering put one question in the exam about the experiment. Okay, one question. And also, there'll be around 20 questions, right? 5% of the exam is going to be a question about the experiment. Let's do this way. Okay. Let's plan for now. It's gonna be an easy question, so make sure you pay attention what we do here and you understand, you try to visualize in your mind how this experiment is done. Okay, and Musa, are you there?
Yes.
Spreadsheet, everything.
Yeah, I did download it, but does each of us need to submit the spreadsheet?
No, it's one per group. The spreadsheet per
Okay.
one spreadsheet per group. Okay. And
Okay.
JPL, have you ever been a JPL open house?
No.
No, right? Okay. And next one, Daniel.
Yeah, I'm here.
Okay. Did you get the spreadsheet, Daniel?
Yeah, I have it.
Okay. Have you ever been an open house there at JPL?
Nah.
No, oh man, you gotta be there. You gotta be there. They have a mission control there. I visited the mission control JPL where they keep on monitoring the spacecraft that go to the other planets. Okay, it's really interesting. David Nwabo, are you there? Good. Spreadsheet. You download the spreadsheet?
I'm about to have it.
Yeah, make sure you get it. Okay, I'm gonna put an N here for now. Okay, have you ever been at an open house, JPL open house? I don't think you haven't, right? Your brother haven't been.
I've been to many open houses, but I don't know the one you're asking about.
JPL is the Jet Propulsion Laboratory there in Pasadena. It's a NASA center. It's the NASA center, one of the NASA centers. Here in California, we're very fortunate that we have 3 NASA centers. Okay, one in Pasadena, another one in the desert near Palmdale and Lancaster, and we have another one there in the Bay Area. You know, in California, we are a fortunate place. Okay, so Zachary Blue, did you get the spreadsheet, Zachary?
Yes.
No, I did.
Okay. Let's see, I'm getting confused here. Let's see, Zachary, are you here?
Yes, I'm here.
Okay, good. You get the spreadsheet?
Yes, I did.
Okay, good. Have you ever been at JPL open house, NASA JPL open house?
No, but I would like to go.
Yeah, check, monitor their website, see when they have one, you know?
Okay.
Maybe we go there as a group, huh? Gotta do that again. Long time I have been there for one of those open house, maybe 10 or 15 years ago. Don't even remember. No, it was even more. It's 20, just 20, more than 20 years ago. I have been one of those. Okay, yeah, just before 2003 that I went to this one of those open house of JPL. Elena, are you there, Elena?
I'm here.
Good. Spreadsheet. Did you get a spreadsheet?
Yeah, I have it.
Okay. Have you ever been at JPL open house before?
No.
Oh, too bad. Too bad. Okay, so put that in your list to do. Right, your to-do list. Doesn't have to be tomorrow. Don't have to do that 1 year from now. We can wait. Okay, so Luis Crystal, are you there?
Yeah, I'm here.
Did you get the spreadsheet?
Yes.
Okay.
No.
No. Oh, too bad. Too bad. Most of you. Okay, Dave Mess, are you there?
Yeah, I'm here.
Okay, first that you're there. If you got the spreadsheet.
Not yet. I'm not by my computer.
Okay, so go ahead and get it. And have you ever been at JPL open house before?
I have not.
Oh, okay, too bad, too bad. Okay, Robert Faust, are you there, Robert? Okay, good. Did you get the spreadsheet? Yep. And what about the JPL open house? Have you ever been there? No. Oh man. Okay. Daniel, when I was a kid, I was obsessed about NASA. I used to live there in Brazil. I used to write to NASA. They would send all sorts of nice things to me. I was obsessed about NASA. I couldn't visit JPL because I was there in Brazil, right? But Daniel Freire, are you there?
Yes.
Okay, good. Spreadsheet?
Yes.
Okay, JPL open house?
No, I have not.
Oh gosh, I'm feeling depressed here. Here you go. Olivia Kroger, are you there?
Yeah.
I'm starting to feel depressed here. Nobody has been at JPL open house before. Okay, a spreadsheet.
Yeah, I have it.
Okay, JPL open house?
No.
Okay. I'll handle that. I'll handle my depression. Here you go. Chuck Lu, here you go. Are you there?
Yeah, I'm here.
Okay, spreadsheet.
Yeah.
Okay, JPL open house.
No, unfortunately.
Oh. You're all making me very sad. Here you go, Amalia Gale, right?
I'm here, Professor.
Okay, spreadsheet.
Yes, I have the spreadsheet.
Okay, JPL open house.
I actually have been.
Go, good. You have been. Have you seen that little drop tower that I do not know if they have a drop tower when you went, but when I went, they had that little drop tower. Did you get to see
I don't
that?
know for sure. It was a long time ago.
Okay. Me too. It was more than 20 years ago when I went there. Okay, maybe they don't have that drop tower anymore. Tiffany, are you there, Tiffany?
Yes, I'm here.
Okay, spreadsheet.
Yes, I have the spreadsheet.
Open house, JPL open house.
No.
No, I'm assuming. Okay, no. Anthony Lopez.
I'm here.
Okay, spreadsheet.
Yeah.
JPL open house.
No, but I've been to the Ames Research Center here in the Bay Area.
Oh, yeah. Okay, Ames Research. Do they have a visitor center there at Ames Research Center?
Yeah, they have a museum over there.
They have a museum over there, right?
Yeah.
I went to Ames a long time ago, maybe 30 years ago, 4 years ago. At that time, I was working at NASA Langley, and I traveled to San Francisco. I met a friend of mine from Brazil. We went to Ames Research Center. We could see the space shuttle there outside. Do they still have the space shuttle there outside?
No, they removed it. They're taking down the hangar too.
Okay. It was exposed, the space shuttle was exposed. Maybe it was like 40 years ago that I was there. But I don't remember seeing a museum, a visitor center. Maybe this visitor center that you mentioned is recent. It's a recent one. Okay. Sha, are you there, Sha?
I'm here.
Okay, spreadsheet.
Yes.
Okay, good. And JPL open house ever?
No, I want to.
Okay. So Daniel Liang, are you there? Okay, I'd love to attend it. Okay, thank you. Daniel, let me see. Is Daniel here? Yeah, Daniel is listed here. I'm gonna put a star here. I know he might be away from his computer. Oh yeah, here you go. Yeah, he typed in there. Good, thank you. Sometimes I don't see your chat message here. Download the spreadsheet and love to attend it. Okay, good. Thank you. So downloaded, never, okay. George Risk.
Yes, I'm here.
Okay, spreadsheet.
Yes, I have it.
JPL open house.
No, I never been.
Okay. Brian McNeil.
Yes.
Good. Spreadsheet.
Yes.
Good. JPL open house.
No.
No. Okay, so I'm gonna put no for everybody. Now, if there is an exception, let me know. For now, and I'm gonna assume most of you haven't been there, so it should save me time. Claire, Claire Ottinger, are you there?
Yeah, here. Yeah.
Okay, spreadsheet.
Yes.
JPL open house.
And I have not been there.
Okay, Jennifer Ramirez. Okay, download spreadsheet, never been. Okay, thank you, Jennifer. Noah Raymond. Noah, let's see.
Sorry.
Yeah.
Yeah, I'm here. Yeah, I got the spreadsheet. No, I haven't been to a JPL open house, but it's on my to-do list.
Yeah, okay, good. Okay. Yeah. And don't forget to put skydiving too, right? Yeah, I once met a student of mine, she did skydiving, and later on she married another student of mine. And that's, she's younger than me. She ended up doing that before me, and I would love to do that before I go from this world. Natalie Santiago, are you there?
Yeah.
Okay, spreadsheet. Okay.
Yes.
JPL, yes?
No.
Oh, okay. You go, Meng Shu Zhang. Are you there, Meng Shu? I don't see Meng Shu listed here. Okay, Meng Shu is in group number 7. Okay, I'm gonna put a 0 here because it's not. Nathan Silva, are you there, Nathan? Okay, good. And spreadsheet? Yes and no, thank you. Darnis, okay, am I pronouncing your name properly? Let's see, it's here. Darnis is here. Let's see here. Yeah, it's listed here. I don't see any messages and chat message. Let me put a star. here.
Can you hear me? Can you hear
Okay,
me?
now I hear.
What I'm saying?
Okay,
There we
now I
go.
hear. Good.
Yes.
Did you download the spreadsheet?
Yes, I have.
Okay.
And I've never been to JPL.
Oh boy, you should go. You should go.
Maybe
Caddy?
one day.
Yeah, one day. Okay. And let's see, Cat is here. No, Cat is not here, right? Aidan never showed up. Valencia, Sandra Valencia. Sandra, no. Robert Wald, no, just Robert Faust. And then I got a Olivia Song. Are you there?
Yes, I'm here.
Okay, good. Did you download the spreadsheet?
Yes.
Okay, JPL open
No.
house ever?
No.
Oh, okay. Sarina Lobana. Are you there, Sarina? Okay, yes, I'm here. I have the spreadsheet and no. Okay, thank you. And Alexis.
Here, yes and no.
Yeah, yes and no. Okay, most of you haven't been. Okay, 32. So we have one more student. Why is that? Let me see. We're supposed to have 33 here. Was everybody called? Brian Spino. We're supposed to have, I see 33 students in my list. Either I didn't get everybody's attendance here was present. Let's see. Mengshu, are you there, Mengshu? No, I don't see Mengshu in the list. Either, you know,
He's in the list, but he didn't type.
He's in the list. I don't
Yeah, I
see
see him in the participant list.
Really? I don't see his name here. Here you go. Is that in
He's like, he's in the middle of Tiffany and Roger.
Tiffany and Roger?
Yeah.
Let's see.
It might be different because I see him at the bottom of mine.
Oh yeah, here you go. Mengshu. Yeah. It's supposed to be, yeah, it's at the bottom. Supposed to be alphabetical order, but for some reason it's at the, yeah, okay. So that's him that's missing here. I'm gonna put a star. Okay. And good. So we have everything here. So let's go through the procedure, you know, like the procedure that we do that. What do we need for this experiment before we go through the procedure? First, you know, lab notes. We're going to need materials, right? Materials is bad, it's lash equipment. We're gonna need a string, right? We're gonna need a mass, small mass, preferably. Small mass, string. You're gonna need a ruler. You need a timepiece. Your cell phone. Your cell phone has a timepiece. Cell phone has a timepiece. Just check on the, they have no plan open house. Okay, thank you, Pedro. Not too bad, right? Because most likely they don't have those planned open house because of the pandemic. So sometimes we use also a protractor, although it's not necessary, you know, just to make sure that you have a small angle. There, the small angle that you use is 10 degrees, but as you saw before, can go all the way up to 30, maybe even 40, 41 degrees to get like a 10% error. That's the equipment, very simple. You can get that almost anywhere. Find a place to hang your pendulum. Think about that, it's a very simple device, and yet it revolutionized the clocks, the mechanical clocks. That was beautiful about simple inventions, okay? That's what's beautiful about simple inventions. If you manage to invent something simple, you know, most likely that something simple that you invented is gonna have a revolutionary impact in the society. And that's what Galileo found out. And that's what Galileo saw, right? He visualized. He didn't manage to apply his pendulum to a timepiece, but Christian Huygens managed to do that. What do you have to know about this experiment? Okay, you have to know about the resolution of your measuring equipment. Okay, the ruler is one of them. Measures length. The timepiece measures time. Okay. And for every activity, experimental virtual lab that we are going to do here, you must know the resolution of those devices. And you are going in my, that's what I do different from many instructors. Okay, I like to be conservative in my measurements. Okay, and so what do? I report the significant figures only up to the resolution of the instrument. In the case of the ruler, the resolution of the ruler is, resolution of 1 millimeter. I know that there are rulers out there that has divisions up to 0.5 millimeter, but most rulers that we use, not rulers, let's put that meter stick. For this experiment, a meter stick is more appropriate.
Oh, you know what? I gave it to Praveen. I need to give it to.
Let's see, someone has the.
Sorry about that. That was my.
Here you go. Someone has the mic on there. Okay, and to measure the length of the string, we use a meter stick, which has a resolution of 1 millimeter. And like I said, what I do different here from many professors is that I want you to report, I want you to be conservative how you report the significant figures of your measurements, okay? I want you to report up to the resolution of your instrument, which is 1 millimeter or 1/1000th of a meter. When here you go, we have this spreadsheet here. You have to format it properly. Here is one measurement of length. This thing is 20 centimeters, okay? If you were to report those measurements, all those things that you see here, they are measurements, okay? What is in red, you do not have to report the significant figures. You don't have to report the significant figures, but the units you have to report, all of them, okay? The units you have to report.
So, Professor, do we not need to report the significant figures of the log on the right? Log L and log.
That's right.
Okay.
That's right. Whatever is in red, just like the G and the log of L, the log of T, you don't need to report. Otherwise it becomes too complicated. Okay, too much work, right? The slope, you don't. It's very difficult to find out what's going to be it's possible to find out what's going to be the significant figures of the slope of your graph, but it's going to be very difficult because you have to go through the equations of the regression line, right? And it's a big challenge, right? So I want to save you on that. So here you go. If you were to report the significant, I'm going to give you one example, okay, of the length. In this case, the length is 20 centimeters. Okay, you have to change the format because it is in scientific format. See, this E stands for scientific format. You go click here, right click, format cell. Everybody's familiar with Excel, by the way? Everybody, just type there in the chat if you are not familiar. Yeah. Okay, good. Everybody's familiar. So hopefully you learn more with me in this course. Okay. Excel is a very powerful tool. So here you go. Let's do that again. Click, right click, format cell. Okay, click, right click, format cell. I'm doing that for the students who didn't take the course with me before, right? I used, okay, Google Sheets. It's important that you use the Excel. And by the way, don't change the format Don't change the format of this spreadsheet, okay? Please don't change the format of this spreadsheet. I have a computer program that's gonna correct everything here for you. And my computer program relies on the fact that you use this format. Don't delete lines, don't insert lines, leave it in the way it is. All you have to do is to, put the units, okay? Units here, units right in here as well. Okay. Units, see that? Depending how the table is organized, the unit is going to be in the horizontal direction or the vertical direction. Okay. And okay, so let's look at the significant figures. Measurement. Okay. Significant figures for L. You go all the way down. Again, we are being conservative how we report the significant figures. Oh, font, number. You go here. Don't use scientific, use number right in here. And then you adjust the decimal places. For the ruler, we are going, everything is being reported in the main SI units, meters, seconds, right? And any combination of the main SI units. Here you go. Okay, so that's what how you're supposed to report on the links. And that is documented in my notes in the following format, right in here. See? Digit, 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 digit. For lengths, measure with the ruler, we go to the third decimal place and display it properly. Please display that properly. Okay, what about the timepiece? Most timepieces out there that we have, the cell phone type, go all the way down to 100th of a second. So let's stick to this resolution. Timepiece resolution 0.01 seconds. So your measurements will have to be displayed. Your measurements, remember, measurements have versus results. There is a difference between measurements versus results. Measurements are raw data that you collect with your instrument. Data that you collect with your instrument. And here you go. So if you were to report time, the first time, and what's this time is all about? Is a time for 10 oscillations, right? You're gonna go, just like I said, you're gonna displace your pendulum from by a given angle, small angles, release it, you're gonna count down 5, 4, 3, 2, 1, 0. It is at 0 that you start your timer. And it is exactly at 0 that started your timer, okay? A typical mistake that a student does is that when they're counting down, they go to -2, -1. Instead of saying 0 and press the timer, no, they go straight to 1, okay? I have seen that, a few times. I would say 10% of the groups of the students make this mistake. And as a result, they don't get good data and they don't get a good percentage difference there at the end of the experiment. So here you go. Now what you're gonna do here, you're gonna format this cell. You're gonna make everything is scientific with 0 decimal place. I did that on purpose. I did that on purpose for you to do some work in there, okay? Every number here that you have to put significant figures, I formatted in scientific format with 0 decimal places. So it is your turn to go ahead and adjust. So for the measurement in time, you have to put 2 decimal places in there. That's how you display the significant digit for this measurement. Okay. 10 oscillations. 10 oscillations for this length, 20 centimeters, take approximately 8.29 seconds. And then the group repeated twice, 3 times. Okay. That's what they did that. And those 3 must also be displayed with the proper significant digit. Don't forget the units. Don't forget the units. Some of them already put that for you. Okay? So that's the part of collection of data. So if there is anything core to this experiment, is those 1, 2, 3, 4 columns. Okay? Everything else are just results. That's your raw data. That's your raw data. Okay, that's where the experimental work comes. You measure the length of your pendulum and you measure how long it takes 10 oscillations. Okay?
So we're leaving the averages in scientific.
Oh, we're gonna get there. We're gonna get there. Okay, so now what about the averages? Here are the results, right? Here are the results. Well, what I said at the beginning that everything that's in red, you don't have to worry about significant figures. You don't have to worry about significant figures here. You don't have to worry about significant figures here, right? You don't have to worry about significant figures here, significant figures here. All right, see that? Yeah, but you do have to worry about significant figures here, okay? You do have to worry about significant figures here. That's when you're going to use the rule for significant figures of the results. When you get data, you're going to manipulate that data. You're going to sum, you're going to subtract, you're going to divide, you're going to multiply, okay? And the result of that manipulation must also be displayed with the proper number of significant figures, okay? So at this point in time, you should know how to display the proper number of significant figures of an average, okay? What is an average? An average is the sum of those 2 measurements divided by 3, right? Here you go. Here's the formula here at the top. So you go ahead, apply the rule of sum for significant figures. Everybody remembers that? Okay. Most likely you learned that in physics 37, right? Most likely you learn in physics 37. What we usually find is that sometimes when we sum, sometimes, not all the time, sometimes when we sum a data, right? When you do a summation of raw data, sometimes we increase the number of significant figures. Sometimes we do increase the number, but not all the time. But at least if you had 3 significant figures here, if you had 3 significant figures here and 3 significant figures here, you're going to have at least 3 significant figures here, maybe more, depending on the number that you got, okay? So you have to apply the rule of summation because that's what an average uses. The average uses summation, right? Once you get the proper number of significant figures here, then you can have the proper number of significant figures here as well. Why is that? Because it's t lowercase t average divided by 10, right? That's the period of oscillation. That's the period of a single oscillation. And then you take the square of this value right here. And again, you have to display the proper number of significant figures. But there are other ones, I don't want you to worry about significant figures. Okay? Sig figs. Is that clear? So let's start working on that. Let's start doing what is easier for now.
Wait, Professor?
Yeah.
I have a question. So for all the quantities in the table right there, all we have to do is like rewrite the values so that they have the right number of sig figs.
Yeah.
Okay.
There is more. There is more. Okay.
Okay.
There's more than that. But at the start, right?
Yeah.
At the start. Okay. So here you go. Let me document what you have to do, right? Well, what I like to tell my students is that, you know, first, before you worry about units and significant figures, you know, first plot the graph. I ask my students to do that first, you know. And then we are going to have 3 graphs. Let me see here. First graph. Yeah. The first graph is going to be T in the y-axis and L in the x-axis. Okay. T in the y-axis and L in the x-axis. The second graph is going to be the T square in the y-axis and L in the x-axis. In the third graph, you just plot the log in the base 10 of T versus the log on the base 10 of L. Okay. So let's start with the graph, right? First, plot the graphs. And if you want to do the sig figs, you know, so, and the units as well, plot the graphs. You go 1. Plot the graphs. 3 graphs. There are 3. 3. Work on the units. Sig. I think that's enough work for now, right? And then there are other things that needs to be done too. Start working on that. Plot the graphs. Here you go. What else you have to do here? Plot the graph. There is more. Here you go. Plot the graphs. Fit the equation. Fit the regression equation. Then. Okay. First graph, and what's gonna be the regression equation? First graph. It's gonna be a power fit. It's gonna be a power fit, just like I have here, a power fit right here. First graph, you know, T in the y-axis, L in the x-axis. Power fit. Second graph, T square. Let's see, T square, L. And that can be a linear fit. Linear fit. And third graph, log of T, right? Don't forget it's T average. Okay. And log of linear fit. Okay. Linear. And what else you're going to do? You're going to log. Well, let's start with the graph first, and then I'll tell you what else you do after doing the fit. Okay. Everything okay? Every now and then I'm gonna interact with you to see, ask you questions to see how you're doing and if you're present as well. Okay. Make sure you are in there in real time. Let's see. Is the one? Yeah, that's the one I want. Go. Let's see, Nathan, you're here, right, Nathan? Nathan. I don't see Nathan here. It's like he left. Okay, I have to note. Nathan Silva. Mengshu, are you there? Mengshu? If you can hear me, I cannot hear, man. Just type there in the chat box, please. And okay, so and I'll put it 12:59. Go, not present at 12:59. I'm gonna put a little star here. Who else? So let's go through you all. And Toby, are you there, Toby? Remember, I need to see you present here so we can interact in real time.
Hey, Professor, I have a question.
Yeah, who is that?
Alexis.
Alexis, okay. Yeah, which group are you?
Group 8.
8, okay. Alexis, let's see. Okay, here you go. Yeah, what's the question?
All right, you know, so I'm using a Mac today. You know, when we're grabbing the data for the XY tables for the graphs, do you know what button I'm supposed to push?
Well, that's a good question. Mac sometimes is different, right? But I believe, let me see. Let me plot the graph. The first graph that you want to plot is this one here, right?
Correct.
The average and L. Okay, in the windows, in the windows, you highlight the T, then you press the Control key and highlight the L. You have to press the Control key. I believe in the Mac, you have to press the Command key to highlight the second column. Did you try that?
Yeah, let me try that 1 second.
Yeah, I believe in the Mac, you have to press the Command key. Okay, don't try, you have to press a button. If you try to, don't press any button, when you highlight the L, the other one is gonna disappear. Anybody else have this problem as well?
Supposed to hold it, right?
Yeah, it's supposed to hold. If you press the Control key, right, in the Windows, yeah, it holds. But if you don't press the Control key, the first column is not gonna hold, right?
Right. Mm-hmm.
Not gonna hold. So you have to press the Control key. Little secret, right? That will take some time for us to discover when we first start using Excel. Did you manage to fix that, Alexis?
I'm gonna look it up real quick. It's not working for me, but
okay.
I'll try it out. I'll let you know.
Yeah. So try one thing or another there. Yeah, and if you have a Windows computer, might be easier just to switch to the Windows.
I have it at home. I'm at work, so we only have Macs here. But I'll try it out. If not, I'll finish it later.
Yeah. If you have any problems, with the Mac, just do the following: copy it, paste it here, and then get the T, right? Paste it here, right? But don't forget, you got to be careful, right? You didn't paste exactly the same number. See that?
Yeah.
Why is that? So what do we have to do? Instead of doing a regular paste, you have to do a value paste. See, 1, 2, 3. That's another secret of, now it pasted the right values. Okay?
Oh, I see. Okay.
Because we have a formula here. Okay, when I copied this column, it copied the formula, right? And the formula was applied to those values here. I get 2 separate slopes. I need to see what you mean about that, Ryan. 2 separate slopes. Your group number, which group are you, Ryan? Group 6. Let me get your spreadsheet. You are doing the first graph, Ryan? Are you doing the first graph? Okay, so here you go. T average, Control L, right? Let's see. If you get 2 slopes, you're not supposed to get 2 separate slopes, okay? So let's see, insert. Here you go. See, I'm getting just one graph, right? I do not know what you mean about 2 separate slopes, but let me show you. Oh, I think I know what's the problem. Here you go. Highlight, right? Click on one of the data points. Remember, you gotta get a regression curve that's for power. This thing is not a linear relation. This thing is a power relation. Okay, so right click. Maybe I think I know what you mean by 2 slopes. Add trend line. See the trend? See, that's one of the slopes, right? That you might be mentioning, but you don't want a linear slope. You want a power slope. See that? That's what you want. What about now? And don't forget to display equation chart, display R square on chart. Okay. This coefficient here, right, should be close to half. And it is close to half. Y is the T average, X is the L, right? T average is proportional to the square root of L, and this data is showing that the power on L is close to half. Okay, rarely you're gonna get exactly half here because these are experimental data. You're getting 0.51, it's pretty good. 0.51 is what? 2%, 2% error. Did you fix that, Ryan? Yeah, okay. Did you find out what was the problem? It's important that you make a mistake, you figure out why you made that mistake, provided you don't spend too much time figuring that out, right? Sometimes it's very difficult to find out where we made the mistake. So we usually move on. But it's important to figure out where we made the mistake so you don't repeat the mistake again.
Hey, Professor, can I ask you to go to where you wrote down where we're gonna do the 3 graphs, the values, just so I can take a screenshot real quick?
Sure. Here you go. Here you go.
Awesome, thank you. So the first values are the X and the L's are the Y?
There in Brazil, I learned the first is Y and the second is the X, okay?
Gotcha,
when I
thank
was
you.
taught math there in Brazil, they taught me that the first one is the Y, right? I have seen here in the United States all the way around. Third graph, log of T average. Oh, I didn't finish it here. Fixed. Okay. Versus, oops, log of L. How did you get the values for the second column when you drag two columns in a separate place? Oh, okay. Yeah, here you go. Let me do that again. Okay, so here you go. I'm gonna copy this one, right? And paste here. This, I gotta copy the heading as well. Now think about, look at that. You know, this T here is not an actual number. It's actually, in reality, it's a formula, right? Right? It's a formula that's referring to this column here, right? If I copy the formula, if I copy the way it is and paste without doing anything special, what's it gonna do? He's going to paste the formula and we'll be referring the formula to whatever is to the left of the quantity, right? So how do you fix that? Okay, how do you fix that? Well, you fix that by using a feature in Excel. You copy, go ahead, copy normally. There's no. And then when you paste, you're gonna use a special type of paste. See that? Paste options. You have the regular paste, and then you have this value. You paste only the value. See that? So the formula doesn't paste into there. So here you go. Now you don't have a formula there anymore. See that? I can even put it with the format. So you're gonna see is the. I'm gonna put 3 decimal places here. It's not necessarily the right number of decimals that we have in there. You can see the numbers are the same. Okay. So what I did here, I pasted the values. It doesn't give you the option, really? Oh, whoa. Do you have a Mac or you have a Windows? Oh, a Mac. There might be another way to access, okay? In the Mac, there'll be a different way of accessing that. Yeah, that's right. Make sure you're not using Google Sheets. Good point, Haroon. Yeah, that's true. If you are using Excel, you know, the instructions for the lab. Okay.
Professor?
Yeah.
I'm having a similar problem, and I'm also on Mac, to where I can like copy it, but when I paste it over, it won't give the values. And I don't think I can find a special options paste option on Mac.
Okay, so
I have a
yeah.
quick solution for you if you're willing to listen.
Yeah, sure.
Just grab the values of one of the say like the T average, and just create a graph, and then click on the points, right click and select data, and then you can fill in the other column.
Oh yeah, you can do that too. You can do that too. Good point. Good point.
Okay, I'll try it. Thank you.
Yeah. Okay. But you know, try if you say you can do. You know, the easiest way is just to try the command key here to highlight the second column. If you cannot do that, then the other option, you know, the other option would be just to type each number separately here manually, right? That would be the other option. It's lots of work, but that's a possibility too. But many of my students who use Mac, they didn't have this problem. Okay, eventually they would be able to use the Control key to highlight the columns separately. So let's see, you go insert, right? Here you go, there's another way, right? There's another way. Here you go, we plot, right? Just by highlighting a single column, that's a possibility, right? That's a possibility. Are we getting the copy of the lab instruction? Okay, here you go. We have a lab manual, okay, SHA. Okay, but let me see what I can do. This is some of the instructions that you can get as well. Let me post there in the Google Drive if you need that. Let's see here.
Professor, for the third graph, what is the x?
Yeah, the x is log of L.
Log of L. Okay, got it.
Let me see. Yeah, log of L right here. So all you gotta do is highlight those two. Right? Let me post those notes here for you. Okay, here we go. Save. PDF. That one. Let's see here. Okay, I'm gonna post this document that you saw there in my Google Drive, the share folder, right in here. And every now and then, I'm going to update those lab notes. It's 1:15. So let's see how you all doing here.
Professor, I have a question about the units.
Yeah. Mm-hmm.
So for log of L and log of T average, you have the units as 1 in your spreadsheet. Is that correct, or do you want us to change it?
No,
Since
no,
it's
that's correct. Yeah, that's correct.
Okay.
Yeah, those functions has no units whatsoever. Okay, those functions.
Oh, okay.
Okay. The argument of any function shouldn't have any units. So actually, what you're supposed to have here is L divided by 1 meter. Okay, and in this case here is T average divided by 1 second. But I didn't want to put the other one in there. So, but any function, the argument of any function shouldn't have any unit. And when you take the function of whatever is inside the argument, you will be a unitless unit. That's what unit is. That one is, right? One is a unitless unit. Unitless unit. Okay. So Sha, I uploaded the document that you asked for.
Can you please share the folder with us, please? I couldn't find it.
This one here?
The folder, yeah, the folder you shared.
The folder.
Yeah.
Okay, the share folder. Here you go. Let's go for the share folder. Do you have the link for this folder? I share.
Let me double check because I didn't find it.
Yeah, let me get the link just in case you didn't get last time. Copy link. Done. Okay, I'm gonna send that to everybody again. Link to shareable folder in my Google Drive. There you go. Here you go. Since most of you are doing that for the first time, maybe we're going to split this lab into 2 meetings, okay? Basically, the major difficulty here is how to plot graphs, how to, use power for the third graph. No. The third graph, you don't use power. You don't use power. It's power fit only for the first graph. Okay, so let's go back here. Power fit only for the first graph. See, power fit, linear fit, linear fit. Right in here. Okay. There is a reason why you cannot use power fit for the third graph. I believe that's because you have a negative values there. Okay, Ryan. 3 different graphs. Make sense, Ryan? Make sense? Does it make sense?
Just another question, Professor.
Yeah.
So the T average is the y-axis or the x-axis?
Okay, here you go. The T average, yeah, y-axis. See?
Okay, perfect.
This format here that I use.
Awesome, thank you.
Y versus X. That's how they taught me there in Brazil, right? I do not know. Some students here tells me that they were taught all the way around here in the States. It's getting hot here. 118. We have another 40, 50. Yeah, 40 minutes to go. Let's.
Professor, how are you
Yeah.
gonna do hard copies? Like, are you gonna sign off the Excel sheet or?
No. It's a hard copy between quotes. Okay. What you're gonna do? You're gonna do a Word document. A Word doc. That's what I call a hard copy in that format that I mentioned in the.
Yeah, but we
right. Okay.
Yeah. We used to add the page, right, that you signed off at the end of class. We just don't do that this time.
Yeah, that's right. Yeah, that's right. Let me see.
Okay.
It's in the syllabus. It is in the syllabus. Let me see here. Thank you for letting me know. Where is that? What is that? You're talking about the syllabus, right?
Yeah, like in 38, when you had us do the hard copies, it was a Word doc, but like the last page was
Yeah. 38 was different, right? 38 we're doing the lab and on the spot. Yeah, 38 we're doing the lab on the spot. So when we do here those virtual labs, I just keep track of whoever is attending here and okay. I still have to upload the videos there to my YouTube, okay? To my YouTube account. You have the link here, right? Here you go. I'm gonna do that in the weekend. Oh, actually, I can do that right now. Okay. So do we have the link there, Daniel? Yeah. Okay.
also, Professor, are you still like clearing us to go after you check our spreadsheet or?
Yeah. Let's do that. Why did you finish already?
Yeah, group 2. It should be. Let me upload.
Okay. Okay, so let me go through the roster, right? And then if you finish, I'll let you go. I'm not gonna check if you did everything right, right? Because otherwise it's gonna take too long. So let's see here. Let's start with Toby. Are you there, Toby? Yeah, I don't see Toby here anymore. Okay, so I'm gonna what I'm gonna put it here as a star. Okay. I'm gonna put 121. Now Pedro Flores. Are you there, Pedro?
Yeah, I'm here.
Okay, so do you have any problems? Did you finish everything? How are you doing there?
I'm still working on it.
I should work on that. Okay, still
Yeah.
working. Status. Okay, working. Kenny?
Yeah, Professor, I'm still working on it too.
Working. Okay, good. Nolan?
Yeah, I'm still working on mine.
Okay, good. Harun?
Here. Also, for clarification, this is due tomorrow.
No, let's see. Let's see how we finish. It's gonna be, let's see, tomorrow is Thursday, right? Let's keep it tentatively to Monday. Let's see how things goes on today. And
The same day, right?
Yeah, let's keep it tentatively to Monday, okay? Next Monday. So you have a little bit of time to do that. It'll be too much work to do that for tomorrow. So are you working on her room? Are you finished?
It should be done. We'll probably make final revisions later, but
Okay.
it should be complete right now.
Okay, so I'm gonna log it here that you're done, and if you wanna leave, that's okay. Musa? Hello, Musa? Yeah, looks like Musa walked out the way. You go. Okay, good. Are you done, Musa? Yeah, okay, so I'm gonna put it. Daniel?
Yeah, still like, almost done.
Almost done. Okay, I'm
Yeah,
gonna
just
put working.
review. Yeah.
Okay. Dave?
Yeah, we're reviewing. We are done virtually.
Working or done? What did I put? I'll put here working, okay? So Zachary. Where is Zachary? Zachary is listed here. Hi, Zachary. Oh, you're working. What are you doing right now, Zachary? You're plotting the graphs. What are you doing? Okay, I don't hear your answer. Let's just relearn. Relearning Excel. Okay. Okay, Elena. How's your status there? What are you doing?
I'm still working.
Okay. Did you plot the graphs already?
I'm on the third one right now.
Okay, third graph. Good. What about Luis Crystal? Crystal. Hi, Crystal. I need to hear from you. Okay, so let me put here a star and not answer, right? I'm gonna put not answer. Not present, not answered. You go. Crystal, 1:25 p.m. Next is Dave. Dave's mass. Mass, right? Are you there, Dave? I don't see Dave here either. So I'm gonna put it 125. Robert, are you there? Okay, what you're doing right now? Finish the graph, okay. Finish graphs, okay. Now you should work on the units and the sequence figures, right? Daniel Frady.
I'm working on stick figs.
Sig figs, okay. Sig figs. Olivia?
I'm still working on it.
Which one? What are you working on?
On the graphs.
Oh, the graph, okay. Which graph? Second, first, third?
The first one, because I just downloaded Excel and it took a minute.
Oh, let's see. Okay, Chuck Lou.
I'm still working on the graphs as well.
Well, okay, which graph?
I'm redoing the first one because I think I graphed it incorrectly.
Okay. Amalia Gale.
I'm here, Professor.
Okay, so what you're doing right now?
I'm trying to fix my Excel. I downloaded the graph and some of the numbers are just like pound symbols. So I'm trying to figure that out right now.
Okay, let me see, you're group number 5, right?
Mm-hmm.
So you're having problems with the data in my Excel file, is that what it is?
Yeah, I downloaded it from the Google Drive, and I think since we opened it in Google just to look at it,
okay,
got converted, and
okay.
Now I have to like fix the numbers.
Okay, you might want to re-download it again, re-download it again. Let's see. Let me just in case, right? Just in case, let me see if there is any problems. Summer roster. Let's see.
Or if you could just send that to me again. I know I gave you my email a while ago.
Okay, can you just download from the group folder? Your group number 6, right? Here you go.
Number 5.
A 5? Oh,
yeah.
5. Let's see. Oh yeah, 5. Here you go. Try to download for a second time. If you still have a problem, then I will email that to you. Okay.
I'll get it fixed. It's no big deal.
Okay, so here you go. Group 5, right? Let me see. Sometimes it's my file that has a problem. Let's see if this one has a problem. Oh, wait a minute. Oh, there is a problem here. You have the incorrect data. Oh, that was my mistake. Oh, no, wait a minute. No, that's lab 5. Sorry. It's lab number
Professor, the problem is that I accidentally changed the format of the thing. So, and I fixed it back. I will upload the new one.
Okay.
Yeah, I changed the format to numbers from scientific.
Okay, so here you go. That's your group. That's your group file. Okay, so you fixed that? That's what you're telling me?
I did, yes. I'm gonna upload the new one, yeah.
You're the same group as Amalia?
Yes.
Okay.
Yeah, we're working together on doing.
Yeah, here you go. Yeah, so everything seems to be fine. Okay, everything seems to be fine here. Okay, so that's the incorrect one. Now let's see. The downloading, right? Downloading. Tiffany?
I'm still working on it.
She's working, okay. So just for me to have an idea, are you working on the graphs? What you're doing exactly?
I'm working on the graph.
Graph, first, second, or third?
I'm on the 3rd right now.
Okay, good, 3rd graph. So let me see, can you share the R-square? Oh yeah, that's right, I got a post in there. Okay, do you know how to do that, Daniel? Do you know how to work on the confidence level? Let me put there, most of you still didn't get to this point, right? Let me spring P37, shareable folder, confidence level. Okay, move. Shareable folder, P37, spring, summer, shareable folder. Okay. So for those students that are still struggling with Excel, your priority is just clear up the Excel first, then worry about this table later on, okay? Move here, the confidence, okay? So it's in there, supposed to be there, Daniel. Confidence level, okay? So Anthony Lopez. So you're still working on the form. Are you there, Anthony Lopez?
Yeah, I'm here. I'm working on the 3rd graph.
3rd graph, okay. Do you have any of that problem that Amalia had or not at all?
No, I didn't have any problems.
Okay. Okay, Shah. I believe
Yes, Professor. I'm almost done with the 3rd graph.
Okay, 3rd graph. Okay. Do you have the same problems that Amalia did or not at all?
No, I was the one who created the problem. So
okay. Don't feel bad about that.
I fixed it back and I uploaded it. So
okay, good. Yeah, when something like that happens, it's just better to start from scratch, right? Downloading the graph again and download the spreadsheet again. And so
I changed the format, so I had to fix it back to the original one. That's all.
Okay, good. So provide solution. Okay, yeah, Musa, if you want to leave, you can leave. So let's see here, Musa. You're done, yeah? Done. If you're done, you can leave. Now, Daniel Yang. Okay, I just finished the graphs. Okay, So what are you working now? Are you working the sig figs and the unit? I suggest that you start working on the units first, okay? First the graphs, then the units, and then the significant figures. That's you know. Oh, and by the way, one more thing, I have to work on this. Oh, one more thing that I didn't note, see, that I didn't tell you. You know, after plotting the graphs, make sure you log the values here in this table, right? The first graph is going to have a coefficient there. So you got to type the value of the coefficient, and it's going to provide you with a percentage difference between your experimental value and the theoretical value. Okay, so let me here write my lab notes. Fit the regression equation. So second, plot the graphs, you know. Log the coefficient, slope. What else do we have to do there? Coefficient, slope, and intercept in the next set of tables, in the next set of 4 tables. 1, 2, 1. Yeah, in the next set of 3 tables. N values the number of data points. N values the number of data points in your graph, right? So you have 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay, so log the coefficient, the slopes, and the intercept in the next 3 tables. That's what, and then yeah, and then you work the units and the sig fig. There is more, but let's. I don't want you to overwhelm you yet. Don't want to overwhelm you right now because what's coming next, most likely you're not familiar with. Okay.
Are you checking our graphs, Professor?
Oh, let's see. No, I'm going to ask you what's the percentage difference you're going to get. Okay. Who is that, by the way?
Alexis from Group 8.
Oh,
I
okay.
uploaded the graphs just in case.
I uploaded. Okay. Let me go through the roster first and Daniel. Okay. Finish the graphs. Okay. Sig figure. Finish graph. Good. George Risk. I don't see George here. Okay, so I'm going to put the star right in here. And that's 136. George, if you're here, let me know. Okay, next. Oh, wait a minute. I put, yeah, George. Good. Next is Ryan. Ryan, are you there? Still working? What are you working on right now? The graphs, the second, the third graph, which one? All of them? Oh, simultaneously? Okay, I'll put the third graph here. Okay, Claire?
Yeah, I'm still working on the first graph.
First graph, okay. What, anything that you need help?
No, it just took me a while to get Excel up.
Oh, let's see. Okay, Jennifer Ramirez.
I have a question, sir.
Okay, 6 feet. Okay, did you get the percentage difference, Jennifer? On the other 2 tables? Oh, we're gonna get Max sheet and let's see, too many messages hanging there. I need to minimize. Jennifer, did you manage to get the percentage difference in the other 3 tables? Not yet. Okay. Okay, good. Now I need the Minimax sheet and the lab notes. Okay, so here you go. I uploaded, it's uploaded there, Ryan. It's uploaded there in the shareable folder. See, confidence level here and the lab notes. Download them, please download them, okay? The units for periods should be don't forget all the units that we're using is the main SI unit. Okay, so what's the coefficient, right? Let's take a look at the coefficient. Let's plot one of those graphs. For the first graph, lab 1, T average and L. Okay, insert. Okay, this one you have to fit a power curve, right? A power equation. Add trend line, go to power, display equation chart, display R square value. Okay, you do that. Okay, that's no, wait a minute. We're gonna get there. We're gonna get there. Hey, there. The coefficient applies only to the first graph. Okay, the coefficient applies only to the first graph, Ryan. Okay, so you go ahead. You go. The coefficient is this value right in here. Okay, is this value right in here. So you go ahead. You log the coefficient right in here. 2 point whatever. 2.0168. Okay. In this case, for group number 6, right, is 2 point whatever, right? The theoretical value is supposed to be something like that. That's what the coefficient is for the first graph. What about the slope? The slope, you know, right? The slope, you know how to do it, right? Here you go. For the second graph,
sorry, can you go over the coefficient again real quick?
Yeah, coefficient. Here you go. First graph. The coefficient is for the first graph. See, T versus V, T average versus L. See that? Okay.
Right.
Okay. Don't worry about this table right now because it requires some more information. But you can do this one here. Here you go. I'm going to plot the graph again. T average and L. Insert chart. Here you go. Click the data points. You have to do a power trend line. Power. Okay. Display R squared, display equation. Did you do that?
Yes.
Okay. So the equation that you're going to get is going to be different from that. It's slightly different from this one because this is the data for group 6. Okay. Which group are you?
Group 8.
8. Yeah. So most likely it's going to be a different value. That's what I call the coefficient. Okay.
I got the exact same value.
Which group are you? Which group are you? 5?
Yeah.
That's group 6. Yeah, sometimes I repeated. Sometimes there are 2 groups that have the same data. Sometimes, sometimes. Okay. So don't worry about that. Okay, what about the intercept? We're gonna get there, right? So that's for the coefficient. Now, notice one more thing. The power here. See that? The power? The power is very close to half, right? Which is what you expect for the square root of L. Okay. Now, what about the other? Okay, so the slope, you know how to do the slope. First, the next graph is going to be, I'm going to delete that, okay? So I don't get too much stuff here. T square versus L, okay? That's the second graph. Second graph, here you go. Supposed to be a straight line, okay? Because I'm squaring a square root. Let me finish that, Claire. Remind me soon. Let me finish this one and then I'll talk to you about that. Here you go. That's the slope, right? That's the slope. But I don't want here is the intercept, right? I don't want the intercept for the second graph. I want, I'll be posting the lab recordings. I don't, let me see, am I recording, by the way? Yeah, I'm recording. That's good. Okay, so this is slope here. You are going to log right in here. And then you're going to compare to the theoretical slope. You're going to get a relatively small delta percentage difference. Okay. What about the intercept? Okay, we gotta plot the other graph. We gotta plot the other graph. What's the other graph? It's this one right here. Did you plot this graph here? Okay. Ryan, yes. Okay, so let's plot it. Let me erase this one first. Okay, erase this one first. And then, okay. Regression equation, add the trend line is going to be a linear one because we took the log on both sides, right? And here you go. That's the slope, right? That's the slope. What's going to be the intercept? The intercept is this value here. Okay, Ryan? Here you go. Intercept experiment. I'm getting 0.34. No, 0.304. Pretty close, right? If I put 0.304 here, you go 0.3047. What percentage difference I get? I get only 0.71 percentage difference. Pretty good. We have pretty good data here. Like I said, it's a simple experiment and it's very reliable one as well. We get very small percentages differences. Okay. Yeah, so let's see if I missed any messages here. Did you get what the intercept is, Ryan? Is the intercept of your linear fit of the third graph. And how do we do the mean and max? Okay, we're running out of time, Daniel. Let's talk about the mean and max next time, okay? Let's talk. Today's Wednesday, right? I'm going to cover that tomorrow because there won't be time enough to do that right now. It's 1:45 already, okay? And let's finish, everything that you know how to finish, okay? And then tomorrow we talk about the CL mean, which is the confidence level. This must be new idea, new concept for you all, but it's a very important concept, CL, confidence level. What about the intercept? Yeah, so let's talk about the CL mean and max tomorrow. Okay, I'm gonna post the recording soon, so bear with me. And you have the link right from my YouTube channel. Yes, I'll be posting everything that I record. Sound good. Oops. Okay, good. So let's see. Noah, are you there, Noah? Good, work on the second graph, okay. Yeah, we got now. I was expecting that, yeah, I was already predicting that we couldn't finish everything today. So we'll continue now because some people are still plotting the graphs, right? Okay, next, Natalie.
I'm still working on it. I'm still plotting.
Okay, plotting, okay, graph. Anything that I can do to help you, Natalie?
Oh, I'm just trying to relearn Excel right now.
Uh-huh. You're using a Windows computer?
Yes.
Okay. Meng Shu, are you there, Meng? Let's see, I can't hear you. I can hear Meng Shu saying, yeah. Looks like Meng doesn't have a microphone. If you can hear me, Meng, just make sure just type there in the chat box because I cannot hear you. Okay, and I can see here in my window that your mic is not active. How do you put x-axis data into the y-axis? Well, you don't have to do that in this lab, Nolan, because everything is already organized in the proper order. Okay, so here you go. See, the T average is on the right side of the L, so automatically the T is going to be in the y-axis, the L is going to be in the x-axis. So I designed this spreadsheet so to make make things simpler for you in the plotting, okay? T square is on the right side, L is on the left side, same for the log, right? But if you want to invert, if you want to invert, all you gotta do, you gotta plot it. You don't need to do in this lab because everything's already set up properly, okay? Click on the data points, everything is highlighted, right? You go, right click, select data. That's the option that you have to select. And then here you go, if you want to invert the axis, highlight the set of data, add it, and then here you go. What you have here. Here's the title of the series. Here's the X values. Here is the Y values. See that? The X values are in the column J. The Y values are in the column K. All you have to do is to switch. What's J? What does J become K? What's K becomes J? If you want, if you need to do that. In this lab, you don't need to do that, okay? But that's how you do it. Okay, so let's see. One more. Make sure, yeah. No answer. Next, Nathan. Is Nathan back? Giving Nathan another chance. No, Nathan. Okay. Go. 149. Tanis, are you there?
Yes, Darnies.
Okay. Okay, do you need any help? Can you tell me where you are, what you're doing right now, please?
Currently what I've done is I did 3 of the charts and I was just making them look nice, but my group mates already put something in there. So we're gonna have to work on our forms of communication. So we don't have one person.
Okay. Okay, so you managed to plot the graph, but there is something wrong, is that right?
There's nothing wrong, just someone is kind of doing all the work and we're not communicating. So we just want to make sure that we're on the same page.
Okay, so we have 10 more minutes to go. So let's see here. Olivia, are you there, Olivia?
Yes, I'm here.
Okay, so what you're doing right now?
I'm working on the 3rd graph right now.
The graph, okay. Okay, good. So you managed to do the other 2, and now you're doing the 3rd one. Okay, so Sarina. To work on the graph. Okay, I'm gonna assume that you're doing the 3rd graph. And Alexis.
Yeah, I finished the graphs.
Okay, you finished the graph. What are you doing now?
I'm just filling out the units, but I'm pretty much done.
Oh, almost done, huh? Okay, we have 9 more minutes to go. It's okay if you don't finish everything today. I was predicting that you wouldn't be able to finish everything today, so we continue. If you run out of time, continue tomorrow.
Am I okay to leave because I have to work?
Okay, so let's see. Yeah, so let's see. Yeah, if you're almost done, yeah. Okay, you can leave. Now let's see, Ryan. Ryan cannot find it. Okay, so let me share the screen with you, Ryan. Here's the shareable folder, okay? Make sure you have the link for the shareable folder. The notes are this one here. The notes that I'm working on real time. Maybe if you are in the folder, yeah, you need the link. Here you go. I'm gonna make sure you keep the link in a safe place. You're gonna need that. Here you go. Here's the link. I wonder if this link is in my syllabus. I don't think I put that in my syllabus. Yeah, no, it's not. Okay, so go ahead, copy this link, put it. You know, I'll try to put that in Canvas as well.
Professor, a quick question.
Yeah.
So after finish the logging all the values, and then we have to find the percentage error.
Well, the percentage error, you don't have to find the percentage error. The percentage error is already calculated automatically for you. Okay. See here?
Oh,
you have to log the value. Once you log the value, say I'm going to put 2 here, right? If I put 2 here, yes, 0.35%, right?
Okay, I just did it separately. I didn't see that. Yeah, I see that now. Perfect.
Okay. So,
thanks.
Here, it's going to be a little bit more difficult. The other 3, you can do it easily. N, T, and R square. This one, we're going to cover tomorrow. I need to get some water. Let me walk away for a few minutes. Hang it there. Okay, so I'm back here. Any messages? Got it. R square. Okay, R square comes from the plot. Okay, when you plotted the graph, Jennifer, here you go. Here you go. Here's the first graph, right? Insert, chart. Here you go. You highlight, right click, add trend line. Okay, is at the bottom. Yeah, the bottom of the pane here. Display equation chart. Display R square value, right? Okay, so Dave, yeah, did you finish, Dave? Yeah, so 3 minutes to go, right? So yeah, you can leave it. Yeah. Anybody else has any questions? We're almost over. So the first time established that decimal place and the rest of the square.
Darnice, are you on here, Darnice?
What did you say?
I'm trying to talk to one of my. Hey, check your Canvas inbox. I sent you a link to where the other group members are communicating.
Great, thank you.
Okay, so. Hashtag. Okay. Okay. So let's see. Let me go one by one here. Ryan's first, right? The first time established. Yeah. That's right, Ryan. It's you know, you have the sequence figures for T1, T2, and T3. The average, you know, how do you get sequence figures for the average? Okay. You get the sequence figures of the average by using the rule of the summation, right? The summation rule. You add T1, T2, T3, you get a result. You determine how many sequence figures are there in that summation. Okay. And that the number of sequence figures in the summation is going to be the number of sequence figures in the average. Okay. That's the rule of the summation. What about that? Daniel, when I try adding sig figs to T1. Okay, the hashtags is easy to solve. Okay, Daniel, are you still there? Is Daniel still there? Okay, here you go. Yeah, the hashtag is easy to solve. Let me show you what happens. When you, okay, do you see that? When you don't have enough space in the cell, it turns into hashtags. Okay? Hashtags is an indication that your cell is not wide enough. Okay? Okay, so what you have to do, you have to increase, you know, the width of the cell. Either increase the width of the cell or, you know, shorten or decrease the number of decimal places in your value there, in your numerical value. Yeah, it's because the cell is too small, it's not wide enough, right? Okay, here you go. So yeah, let's do min and max tomorrow because it's gonna take some time. CL min and max tomorrow. Okay, Robert. Okay, so thank you. Okay, so it's 2:00 p.m. right now. So I have our office hours right now if you want to stay around. Otherwise, I will see you tomorrow.
Thank you, Professor. Have a great day.
Yeah, you too.
So Professor, for T1, or no, not T1. So for T1, use decimal places, and then you take what you got from T1 for significant figures of T1 to T2.
Yeah, because it's the all T1, T2, and T3 were our measurements that were done with the same device, right? Your time.
Yeah, but you don't use the decimal places of T2 and T3. You just use the significant figures of T1.
Oh, you let's see, here you go. Let's put it, let's you know, you gotta put it in numeric format, right?
Yeah.
You know you have to go up to the second decimal place, right?
Yeah.
Okay. And now when you sum those three numbers, you are going to display up to the second decimal place too, right? Here you go. I'm gonna sum those three units, those three values. Here you go.
Is that what you do? Type in equals sum.
Yeah, that's right.
Okay.
And now I'm going to display the summation with the right number of sequence figures. You must go to the second decimal place. See that?
Yeah.
How many sequence figures do you have here?
3.
How many you have here?
3.
How many you have here?
3.
How many do you have here?
4.
Yeah. So your average, you're gonna have how many sequence figures?
3.
No.
Oh, 4. 4.
It's gonna be 4, right? Because the average is this value divided by 3. Okay.
Okay. Oh, I get it. And
So you
then
gain, in this specific measurement, you gained a significant figure. It doesn't always happen, but sometimes it does. Okay.
so how do you add them up like you did instead of doing it manually?
Well, you just, here goes, sum is a function in Excel. See that? Here you go. Take a look here at the top. At the top, equal sum, open parentheses, highlight T1, T2, and T3, close parentheses. Okay.
So sum, open parentheses, highlight T1, T2, and T3.
Close parentheses. And then it does the math for you. Okay. Okay. If you're talking, I can't hear you, Ryan.
Oh, I was wondering, do you copy and paste? Like you do sum, open parentheses, and then you copy and paste the values?
Where? Copy and paste the values where?
So you did T1, T2, T3, and
Yeah.
you did sum, open parentheses. How do you put the values into?
Oh, you just highlight, see that? I open the parentheses, right? The cursor
Yeah.
is right in here. And if I highlight it, you go T1, T2, T3, it does automatically for you.
It automatically does that.
Yeah, Excel
Okay.
does that automatically for you.
And do you have to do capital letters, sum?
No, it
Okay.
can be lowercase as well. Okay. So let me. Okay, so we go. Let me close that. Okay, so we go. I'm gonna close this one as well. Any more questions?
I might have to start all over again. I just messed up my graph. I tried to put sum, and it's not letting me go back. So now my T1 has the word S, the letter S in it, and I can't change it back to what it was originally.
Yeah, you gotta. Yeah, you have. Make sure when you do those things, you do in an empty cell, right? Otherwise, you're gonna lose some information there. Or you can even undo it. If you know, Control Z, you just revert back to what you had.
It doesn't go any further.
Get out of the cell first. First, you have to get out of the cell.
Oh, okay.
First, get out of the cell.
There, oh yeah, I fixed it. I'm so sorry that it's taking me a while to do this. I'm really trying to, like, I did some in open parentheses and I highlighted. Am I highlighting it correctly? Is it like when you copy and paste it?
Oh, well, I do not know what you mean by copy and paste.
So like when you're highlighting it, is it just like you're left clicking it and then you're just like dragging it to the right?
Yeah, here you go. I'm gonna do sum, right? Open parentheses, right? You see it?
Yeah. Yeah.
Okay, so here you go. I'll get to you soon, Jennifer. Hang in there. I cannot go. Okay, now I'm gonna. Here goes sum. Here you go. See, I highlighted the cell.
How does it turn like that? How does it like turn that color?
Well, when your cursor is inside the parentheses, see that?
Yeah.
It's going to highlight wherever you click. Wherever you click, okay?
Okay.
If I want to sum this one with this value here, I gotta put a comma. Here you go. Another one, see that? Comma. Another one. It's gonna be 6, right? If I add this other one, it's gonna be 7, right?
So
7.
wait, the thing is, when I highlight, when I do sum open parentheses, oh, you have to put equals, right?
Yeah, you gotta put the equal here.
Got to put equals. Okay.
Yeah, if you don't
Well, let
put
me
the
try it
equal,
now.
yeah, it's not gonna work. Okay, so let's see, Jennifer. So we do the sum for each row. Let's see. If you do the sum, you don't have to, okay? You don't have to. But if you end up doing the sum, do not change anything here in my table, right? Do the sum on the side in an empty cell. Okay, Jennifer, you're not required to do the sum. But if you do, you know, doing the sum is advisable because helps you find out how many significant figures you're going to end up having, okay? But you don't have to do it. And if you do it, make sure you do the sum in an empty cell outside my table. Make sense? Okay, anybody else need any help? Okay. What the heck is going on here? CL.